here. Sir, unmute yourself, sir, please.
Sir has joined.
Good morning, Prashant, sir.
गुड मॉर्निंग सर, कैसे हैं?
अनम्यूट करना पड़ेगा सर.
प्रणय उधर से कर दूं?
हेलो, गुड मॉर्निंग.
हेलो, गुड मॉर्निंग सर.
गुड मॉर्निंग. कैसे हैं आप लोग?
हम लोग ठीक है सर, आप कैसे हैं?
बस यहाँ तो फॉग हो रहा है.
यहाँ भी हो रहा है बट आज थोड़ा कम है शायद
हाँ,
पहले
यहाँ
से.
ठंड आज अचानक से 1-2 दिन में बहुत ज्यादा हो गई है.
यहाँ तो सर मुझे लगता है 10 दिन से पिछले बहुत हवा और वो चल रहा है जब से स्नोफॉल हो रहा है तब से.
हाँ, यहाँ भी उसका इम्पैक्ट दिख रहा है काफी.
हाँ.
कल तो बहुत ज्यादा वो शीतलहरी टाइप थी यहाँ पे.
हाँ, कल यहाँ भी काफी हवा बहुत तेज थी कल शाम से, मतलब आफ्टर सनसेट.
गुड
तो
मॉर्निंग,
मेरे
नमस्ते
पास
सर.
नमस्ते वरुण, कैसे हैं?
बढ़िया है सर, आप कैसे हैं?
बढ़िया बढ़िया. कैसा चल रहा है सब?
सब बढ़िया से है सर. कैसे हाल बीएचयू के हाल चाल है सर?
बेचू अच्छा है भाई. आज थोड़ा सा 50% कैपेसिटी पे सारी लैब्स चल रही हैं अभी मेरे ख्याल
अच्छा
से.
अच्छा.
अब देखते हैं. स्टाफ तो 50% पे पूरा हो ही गया था. लैब भी उन्होंने 50% पे ही कर लिया, मतलब
ओके
अल्टरनेट
ओके.
कर लिया है.
अच्छा,
क्योंकि
तो अभी तो
केसेस
बहुत कम लोग
अचानक
आ
से
रहे होंगे सर आपकी
पीक
लैब में.
बढ़ने लगे हैं, तो लैब वगैरह कुछ कुछ बंद हो गई हैं अभी.
अच्छा अच्छा. हाँ, तो अभी तो प्रॉब्लम हो रहा है सर थोड़ा.
हाँ, अचानक से ये मतलब वेव आ ही गई है अभी. अब देखते हैं डिक्लाइन कब तक करती है ये. मोस्ट प्रोबेबली
यस
शायद
सर, यस सर.
फेब तक डिक्लाइन कर जाए.
यस सर. और सब बढ़िया है सर, घर पे सब अच्छे हैं सर सब?
हाँ हाँ, सब बढ़िया है. तो अभी कहाँ सब ऑनलाइन टीचिंग चल रही है या फिर ऑफलाइन भी है अभी?
सर ऑनलाइन ही चल रही है सर अभी तो फिलहाल सब.
अच्छा.
यस सर.
एग्जाम्स वगैरह तो फिर सारे ऑनलाइन ही हो गए होंगे.
अब सर एग्जाम के लिए तो ऑफलाइन बोल रहे हैं सर, लेट अस सी सर.
ऑफलाइन.
हाँ.
ऑफलाइन में बहुत रिस्क है सर. जिसने ऑफलाइन रखा था सबने फिलहाल कैंसिल करके ऑनलाइन कर लिया.
सर हमारी कल ही आई है डेटशीट.
यहाँ पे सर बोल रहे हैं ऑफलाइन के लिए, लेट अस सी सर. हम लोग भी सोच रहे हैं ऑनलाइन हो जाए तो अच्छा है, क्योंकि बच्चे बहुत आएंगे बाहर से.
हाँ, मतलब बाहर से बहुत ज्यादा आएंगे और वो अचानक से फिर वेव बढ़ेगी.
पता नहीं सर, देखिए क्या होता
मतलब
है.
ज्यादा और ज्यादा लोग भी वो होंगे.
यस
बेटर
सर.
है कि ऑनलाइन ही कर लो, ज्यादा ठीक है.
हाँ सर, वो काफी बेटर है सर.
हाँ, एटलीस्ट टीचिंग ऑनलाइन मतलब टीचिंग ऑफलाइन रहती है तो ज्यादा अच्छा इंटरेक्शन होता है. बट एग्जाम
जी
में
वो
तो
तो है.
ऑनलाइन कर
हाँ वो
सकते
सर,
हैं, कोई वैसा
वो तो
कुछ नहीं
वो तो है सर, लेकिन अभी तो मजबूरी है सबकी, क्या करे.
है. क्योंकि इस बार काफी नुकसान हुआ है एटलीस्ट स्टूडेंट्स का.
हाँ हाँ सर,
वो
डेफिनेटली सर.
प्रैक्टिकल्स नहीं कर पाए, बहुत सारी चीजें नहीं कर पाए.
यस सर,
जो
डेफिनेटली.
एक इंटरेक्शन होता है 1-to-1 बहुत सारी चीज स्टूडेंट्स का, तो अभी वो भी नहीं मालूम चल रहा है कि कौन है.
यस सर, यस सर, वो तो है सर, काफी प्रॉब्लम तो है. बट देखिए कब तक चलता है सर.
कॉलेज लाइफ दिखा ही नहीं मतलब मास्टर्स का.
हाँ, काफी
ऐसा
काफी
हो
बच्चे,
गया.
बिना आए ही कॉलेज पास आउट हो गए.
हाँ, वही मैं कह रहा हूँ कि उन्होंने कॉलेज देखा भी नहीं. और मतलब
वो
जो
तो है ही है सर.
एक्सपोजर होना चाहिए था जिस लेवल का सॉफ्टवेयर सीखने का, सब चीज़ों का, वो सब सारी चीज़ें नहीं हुई.
यस सर, यस सर.
तो अभी कितने पार्टिसिपेंट्स हैं टोटल यहाँ पे?
26 सर.
सर टोटल 26 हैं हमारे पार्टिसिपेंट्स, जो विंटर स्कूल चल रहा है.
अच्छा. हाँ
बाकी कुछ अपने स्टूडेंट्स भी हैं सर उसमें.
हाँ, ठीक है.
अपने डिपार्ट सेंटर के कुछ स्टूडेंट्स भी हैं सर उसमें.
अच्छा.
Sir, with your permission, we can start.
Yes sir, please go ahead.
Dr. Ms. Upasna, I will please introduce our eminent guest for today. Please, we'll start.
Yes.
Officially, we are going to start our session.
Yes.
I'd like to welcome everyone once again on behalf of Center for Climate Change and Water Research, Suresh Kanviha University, Jaipur, Rajasthan, on the ninth day of Summer Winter School in Geospatial Science and Technology, Level 1 program, sponsored by DST NGP. Now, let me introduce to our first speaker of day 9, Dr. Prashant Kumar Srivastav, sir. Dr. Prashant Kumar Srivastav sir is currently working as an assistant professor in the Institute of Environment and Sustainable Development in BHU, India. He received his doctorate of philosophy in civil engineering, University of Bristol, England, UK. His MPhil in remote sensing and hydrology from School of Environmental Sciences from Jawaharlal Nehru University, New Delhi, an MSc in hydrology in environmental sciences from and School of Environmental Sciences, JNU. His research interest includes mesoscale and hydrological modeling, microwave soil moisture retrieval, radar precipitation retrieval, optical IR, hyperspectral remote sensing, evapotranspiration, sensitivity and uncertain analysis, land use modeling, natural disaster. Previously, he also worked as an assistant professor in environmental sciences in NVPAS Sardar Patel University, Anand, Gujarat, from 2007 to 2010. He was also the visiting scientist and faculty in hydrological sciences, NASA, GSFC, Maryland, USA, and in BCC Noah Crest Geospatial Center, the City University of New York, USA. Also in Department of Geography and Art Sciences from Wales, UK. He has authored more than 160 research articles, 26 book chapters, 19 conference proceedings, 6 books which are published in various peer-reviewed national and international journals that have more than 3,906 citations. His major projects are, are as role science collaborating in NASA SGFC in soil moisture retrieval and simulation of soil from SMAP satellite, working group partner in NASA JPL from SMA calibration and validation, working as PI in Department of Science and Technology on long-term monitoring and precipitation and evapotranspiration for discharge prediction in selected catchment of Kosi River Basin. So with that, I'd like to invite you for this training session and to start with your session. Thank you, sir.
Thank you, Dr. Shruti, Dr. Suraj, Dr. Varun, and Upasna for introducing me. And I'm glad that you are doing this such a informative workshop that is winter school on different aspect of remote sensing. And I hope you participants are really enjoying this workshop and learning a lot from this program. So, starting with my topic, I thought that I will go with the basics of digital image processing, but I think many of other resource person already covered those topics, and it is good to go what is new going on with in this field, like in remote sensing and other field. So today I'm going to cover one of the important topic, that is hyperspectral remote sensing, because most of you already aware of this multispectral remote sensing, how this multispectral remote sensing can be used in different aspects, how we can do simple image processing, pre-processing step like image histogram, contrast stretching, and all those things, because those are the basic things that you will do in your hands-on sessions. So here, what is new with this hyperspectral remote sensing, and why many space agencies are behind this? Because this is one of the upcoming missions that is going to be launched in 2024. Like one of the mission is every Sanji mission that is going to be launched in 24-25. Similarly, one other mission like Prisma, it is already launched, and in the figure you can see this is the HIC mission of our ISRO's HIC mission, hyperspectral imaging mission, that is for moon surface monitoring. So there are some missions available, but all the missions have some pros and cons. And you will see that previous missions are having a lot of noise in their hyperspectral sense data sets, means in terms of water vapor noise, aerosol noise, and other noise. So continuously this field is now evolving, and hopefully within the coming years you will get a powerful satellite for in hyperspectral remote sensing. And towards this, Italy launched his Prisma, and this Prisma satellite is providing you all the hyperspectral remote sensing from space. Similarly, every Sanji mission that I'm talking about, it is giving hyperspectral data through aircraft. So things are going on, and this aircraft mission, every Sanji is you can say the exercise for launching a full-fledged satellite every Sanji in coming years. So what is this hyperspectral remote sensing? So if you see previously, if you go back in 20-30 years, that we have black and white cameras with us. Like whenever you take photograph, you get a black and white images. Like your TV also, you are getting black and white TV quite a few years back. If you go to 90s, you will get all black and white TVs, and then in 90s, 5-4 color TV started. So that time, if you see that black and white TV is generally a gray scale, and if you see the number of band in that is only one, it give you different shades of black color. But if you go with the number of bands that is used in that cameras or in your mapping is only one band. But after some development, you started getting color images. Like if you see your colored camera, that is operating in 3 bands like RGB, red, green, and blue. So why they choose this red and green and blue? Because in remote sensing, you know that RGB is a primary color, and this red, green, blue can be mixed to get a number of colors that you want. For example, if you mix red and green, you will get yellow, red and blue cyan, and then blue and green magenta. So in this way, you can mix different color. Mix primary color, you will get your secondary colors. If you mix secondary color, you will get your tertiary color. So RGB is the uh, first color combination that is launched uh, in your early satellites or missions. And you can see after this RGB band color combination, we are started getting this color image. And then after that, multispectral satellites came into picture. Like if you see Landsat 8, our Indian remote sensing satellite, and then number of other satellite like LIS-4 and all those, you will get multispectral images. And if you see that this multispectral images, it is start from 2 to 30 plus bands, around 30. So like if you say Landsat it is started with 7-8 bands, and it is going up to 12 bands right now in Landsat only. And then Landsat 9 is already launched. It means it is you can say follow on mission of Landsat 8, because Landsat 8 has some life. After a few years of life in the outer space orbit, because of technical failure, battery decomposition, and all those things, next series is generally launched. So from Landsat 1, we are not having Landsat 9 in the orbit. So this multispectral have you can say around 10 to 12 bands. Like it has RGB, then we have near infrared, then we have short wave infrared, then we have thermal band. In this way, we have other bands also in this. So means in SWIR, short wave infrared, you will get 2-3 bands. You will get thermal channel. In NIR, you will get 2-3 bands. So overall, you will get in around 10 to 12 bands in multispectral. Most of the multispectral satellite. Like if you come with this Sentinel, it is giving few more bands than Landsat 8 or Landsat 9. And then after development of this multispectral, now technology is going towards development hyperspectral satellite. Hyperspectral means it's like around 30 to 300 bands. So it is a discrete bands, and this is a continuous band. We will see what is the difference between discrete and continuous in next slides. And then now upcoming is still it is in process, ultraspectral, and it is not yet launched. Not but things are going in this direction to give you a more fine resolution information of your Earth surface. So this way we are up to here, because ultraspectral is still not launched or not in progress. So we don't have any images of this ultraspectral. But hyperspectral we have now with the satellite and other thing. Once it is fully fledged developed, then we will get ultraspectral satellites. So if you see this, what is this hyperspectral satellite? What is this? How we can use this in our work? So if you see that there are three different classes of multispectral and hyperspectral images here. One is, you can say, Landsat ETM plus enhanced thematic mapper. Other one is Aster, and other one is Hyperion. Hyperion is a first hyperspectral satellite mission, and we call it Hyperion. So if we see the lines, this is hyperspectral imaging. This is all your multispectral imaging, and this is from Landsat, and this is from Aster. So in Aster, if you see that number of bands are around 14. Okay, there are 5 band in the thermal infrared region, and in SWIR we have 4 and 5 to 9 bands here, and then in visible near infrared we have 3 bands. Similarly, in Landsat we have 4 band in visible infrared, 2 band in SWIR shortwave infrared, and 1 band in thermal infrared. And Hyperion cover from visible near infrared to SWIR shortwave infrared. So what is the difference between this all the satellite images? For example, if you see your RGB color combination, blue, green, red. So blue is it is giving information in blue band, and then slowly you're moving towards red band, 700 nanometer. So if you should see the visible band, start from 400 to 700 nanometer, and it is a discrete band. Discrete band means for one point it will give you only one information. For example, suppose you need a information over here, so you don't have any bands here in either in Landsat or in, you can see, in your Aster. But hyperspectral mission is giving continuous information in this region also. And why this information is continuous? Because every nanometer it is giving you in data. Like if you see playing cards, you have a different. If you see the card stack, if you see you have different cards in that stack. So one card is your one band. It's like one wavelength. Like blue is one wavelength, red is one wavelength, green is one wavelength. So that is like in image, it is like a one full scene is like a one card. So what you do in image processing, that you stack all those cards and then you plot your these spectra. So similarly in hyperspectral data analysis also, we have different bands, or you can say different cards. And like in Aster or Landsat, you have only 8 cards or 7 cards. In Aster, you have 14 cards. But in Hyperion, you have 264 cards. 264 cards means every time you are getting, each card is giving some information. Means each card is giving you some wavelength. Like if you see your is it clear to you what I'm trying to say?
Yes, sir.
Excuse me?
Yes, sir.
Okay, so what I'm trying to
Yes,
say
sir.
over here, yeah, that each card is giving you a information. For example, if you go outside your lab and you see your vegetation and other thing, that some vegetation are green in color, some are red in color, but some are purple in color. So do you think red, green, and blue cover purple also? No, right? Because we don't have any band or any wavelength to capture that purple wavelength in a Landsat or Aster. But because it is giving taking information of every nanometer, so it is capturing that color also. So with the launch of Hyperion, now you can cover many wavelengths that is possible in your environment up to this SWIR wavelength. But in Landsat and Aster, those bands are missing, or those bands are averaged. Like here to here, it is averaged. So you don't know whether it is in between this set, it is because of red color or light red or dark red or something. And if you see the plants, some plants are light red in color, some plants are dark red in color. Like if you see forest is giving you dark red color imaging, and while agriculture is giving you light red. But here you will get an average value. You don't know which one is light red and dark red. So it is giving average value. But in hyperspectral, it is giving all those color levels also. So like if you see your blue goggles, if you wear a blue goggles, it allow only blue light to pass, right? So you can see the blue color outside. So that blue glass is like a, or blue goggles is like a filter. So similarly, if you wanna see red, then you use a red filter. If you wanna see, use a green filter. So in this way, bands is like a filter. So in hyperspectral, we have 264 different bands to filter out the non-needy bands and allow you only the band that you use in your research. Like red allow only red band, green allow only green band, blue allow only blue band. So in satellite, if you say, it's like a fine optical fibers. So that optical fibers pass allow you to pass only that particular wavelength. In display, in hyperspectral satellite, you have 264 filters in that satellite. In Landsat, you have only 7, 8, or 12 filters. In Aster, you have 14 filters. So what is the use of that filter? Allow only the particular wavelength and block the rest. Otherwise, if allows everything, then it will be like a sunlight. You will not get any information. So this way, HyperIon is one of the best technology that is coming, and now it is going. Prisma is already launched, so it is data sets are available for use. And what I'm saying that it is like a card. If you say each wavelength is like a card, so if you stack your image, you will get a stack like this. And if you cut a particular portion, you will get a square shape element. We call it hyperspectral cube, because this is like a cube. So this hyperspectral cube, each wavelength is here. Suppose this is 0.4. This first card is 0.4. So 0.4 is plotted here. Second is 0.5 plotted here. 0.6 is like this. You can plot from 0.4 micron to 2.5 micron, and then you will get a spectral signature. So this is for 1 pixel. You are getting one spectral signature. Similarly, if you have some different object like forest, you will get different spectral signature. If you have minerals, you will get different spectral signature. You have water, you will get different spectral signature. So each one of the basic principle of this hyperspectral, that like if you see our thumbprint, no two people have the same thumbprint, right? If you put your thumb impression, no two people are having the same thumb impression. Similarly, no two objects are having the same spectral signature. The spectral signature is different. So for example, in one of our work, we're trying to classify, suppose, some minerals. So what happen if you have two minerals like calcite and dolomite? Calcite is calcium carbonate, dolomite is calcium magnesium carbonate. And if you want to take the spectral signature of both are different. If you see with a normal eye, calcite and dolomite both look same because both are white in color. But if you take the hyperspectral signature, because of magnesium in dolomite, you will get an additional absorption in that dolomite that differentiate that dolomite from the calcite. Similarly, with the vegetation also, like if you are going with the species and discrimination or mapping, no two species are having the similar spectral signature. So we use that signature to differentiate two crops, two species, two minerals on a large scale area. So if you see the spectral signature, this is from different satellite. These are all the spectral signatures. So if you see in the Landsat TM thematic mapper, we have only 5 bands: 1, 2, 3, 4, and 5. But with the GARIS, another remote sensing satellite, if you see that because it has many bands, so you are now getting information over here also, because you have only one band here and one band here. In between, there is no information is available. That's why it is a straight line. But when GARIS is launched, you will see that there are several absorption bands over here. And because of this absorption bands, why this absorption band we are getting? Because we have now bands of over here also. We have sensors over here also. But in TM, we have sensor here and here, but we don't have any sensor here. That's why we are getting a straight line. Similarly, this average SNG mission that I'm talking about, it has around 400 bands, not 264, 400 bands. So it is giving you every inch information or every nanometer information of an object. It is like the X-ray of an object. So each and every absorption, whenever you have absorption, you will get these dips. You can see these are the dips. You are getting these because of the absorption of the because of particular element. You will get this type of absorption band. And in remote sensing or in hyperspectral remote sensing, these absorption bands are much important than reflectance, because absorption bands are element is specific. For example, in calonite we have sodium magnesium thing, so because of sodium magnesium maybe this absorption happens, but reflectance can be changed because of sunlight condition, because of other thing, but absorption happens only due to some particular minerals or particular elements in that substance. So in every Sanji, you will see that you are getting more of the absorption bands because you are getting every nanometer information. Every nanometer you are mapping that Earth surface. So that's why you are getting much better and spectra over here as compared to Landsat, in which we have only 5, but here we have 400 bands. And similarly, it is a lab-based spectra that we are doing with our handheld hyperspectral radiometer. So in our handheld hyperspectral radiometer, we have 350 nanometer to 2500 nanometer information, and we are getting around 400, or in our hyperspectral radiometer, we are getting around 1000 bands. So in 1000 bands, it's like you are getting many more important features from a substance. And that's the thing we are doing in our work. We are trying to get this spectra, and then once we have this spectra, we try in the image, we try to find where this spectra is matching with the satellite image, and then with the classification we try to get the elements. So if you see the difference between the discrete bands in multispectral and continuous band in hyperspectral. So if you see that this is a discrete band, so you have one average value over here. We don't have fine level value at each nanometer. And in multispectral, we don't have bands here, we don't have bands here, and only one discrete band over here. So it is, you can use this discrete band for some of the analysis, but you cannot use discrete band for cellulose, scattering, phytochemical, biochemical, some of the minerals analysis. You cannot use because we don't have bands, we don't have any imaging in this range. So this why multispectral is not that okay to monitor all those things. But if you come with a hyperspectral, you have all information over here. So you can now have much better monitoring capability. Now you can do leaf water, nitrogen, different aspect of nitrogen, scattering, chlorophyll, different biochemical parameter. Then you can do more better level of species discrimination. So you can do a lot of things with the hyperspectral, because you are getting a continuous measurement from in this spectral range. So this is one of the thing that this is the average NG airborne campaign image. So if you see, we have 4-5 elements over here. So one is atmosphere. If you turn your radiometer up, you will get atmospheric data. If you want to have vegetation, you will get soil, you get vegetation, you get water, everything you can get. So suppose you have atmosphere. So if you see the spectral profile of atmosphere is different. If you see soil, spectral profile of soil is different. If you see water, it is different. If you see vegetation, it is different. So if you see the spectral signature, it is all very different. Why it is all very different? Because every element has their own spectral signature. And generally what we do, we make a library like this for all the elements over the in the image. Like for species discrimination, we have different types of pine. For example, in one of our forestry work, we have having different species discrimination work, in which we are collecting different species in the Himalayan region, like your Pinus, Texas, and other species existing, Betula, and other many species are existing there. So we are trying to make a library of this, and once this library is here, with the help of artificial intelligence or neural network or different classification algorithm, we try to match each pixel. So suppose here, if you take a 1 pixel over here, and this 4 spectra we will try to match. So here, if this spectra is matched, then will be a forest. If this spectra is matched, it will be a water. So automatically it will classify satellite image. So for broad level classification like soil, water, vegetation, multispectral is okay. But if you ask, somebody asks, what type of vegetation is this? What type of species is this? Then you need to go with the hyperspectral, because you can tell that, okay, this is a pinus strands, or you can say it is a oak strand, or you can say it is a some any other tree species over there like Texas or something else. So for that you need a different library over here. Like vegetation, you need one library for for Texas you need one spectral signature. For other pine you need other spectral signature. So in this way you need different signature, then you can classify. So generally this signature we are taking using our hyperspectral handheld radiometer, ground based. So with the help of the ground based radiometer we develop this spectral signature, and then we try to find the same spectral signature over a large area using our hyperspectral satellite image and our reference library. So I will come to this in a while, but I'm trying to show this is the small instrument that we are talking about. So this is our that we are using here in our laboratory. It is hyperspectral UST hyperspectral radiometer. It is a full range from 350 to 2500 nanometer, and it is for ground sensing. Like every sensor, generally we have three different type of sensor. One is at ground, other one is at airborne, and third one is in the space. So this is ground based sensor, and generally we are using this radiometer in three different ranges, like visual and near infrared we have 350 to 100,000 nanometer, SWIR 1 shortwave infrared 1000 to 1800, and SWIR 2 1800 to 2500 nanometer. And because we are getting every 1 nanometer over here, 6 nanometer over here, so we are getting around 2151 bands through this. But because of some noisy bands, we remove it and bring down to around 1000 bands. So overall 1000 band is quite high as compared to your Landsat, any Indian remote sensing satellite like IRS, LIS-3. So it is giving a lot of information because of this band. But if you see that HIC that is launched by ISRO for Moon mission, that is having 64 bands. And then Hyperion that I already mentioned, that is having around 264 band. Prisma is having around every Sanji is around 400 bands. But it's ground based because we have facility with this, we can customize it at the ground. So that's why we are having around 2000 bands. But in the satellite, if you want to put 2000 filters in one satellite, they'll be very complicated, technically very problematic, because more higher is the number of filters in your, there is a higher chance of getting noise. So that's why it is one of the science that's coming up. If you put too many filters, each filters now may affect signals of other filter, and then you will get some disturbances in your measurement. So science is going on. They are trying to put around 300 filters, 400 filters, so that you can get a high quality of fine level mapping of our Earth surface. So if you come this in the field, generally what we do, we have this artificial light source. Suppose outside it is called cloudy. So we need a source which is giving wavelength similar to our sun. So this is a lamp that we are using. It is one of the costly lamp. This lamp itself costs around 1.5 lakhs or something, because it is mimicking the source like sun. It is giving the same type of wavelength as sun. So, but not at energy. It is only the wavelength in that region. So you will get this light. Then this is a white reference panel. So first we need to take a white reference reading, so that it is giving you a nullified reflectance profile. You will get a straight line over here. So there will be, this instrument is calibrated. Then we measure our crops, or in the Himalaya we measure species and all those things. So this way we are measuring all these measurements in the you can say field or as well in the lab. Sometime what happen if it is very complicated region, suppose this is the hilly region, we cannot go with the instrument to this region because you cannot go simply. It is a quite steep mountain, you cannot walk. So what we do, we try to get a sample from these leaves and then bring it up over here. We do the white reference panel and then we take a reading through this handheld uh, optical fiber. So this way we take reading if we cannot access the region. Otherwise, if we can go, we put this instrument on the back and then we go to the field. We have a gun like this. We take a snap. Sorry, we take a snap and we get a reading of the this vegetation. So similarly, once one vegetation give you one spectral profile. So this is one vegetation. If you go to some other vegetation like paddy or something, you will get another vegetation. In this way, you can build a crop species library. So this is the estimate that we are doing at the ground, and satellite we already showed you on our first slide that is the IC, and through that we are taking the space-bound measurement. So generally, what is the approach that we are using? First, we need to develop a spectral library. By using that radiometer, we develop a spectral library, because if we satellite don't know what is the species level. Okay, satellite don't know what is the species level. So what happened? We need to go to the field and then we first develop a library over there. And library, how we can develop this library? By with the help of this radiometer that I showed you. And for example, in our agriculture field, that in BHU, we have different species. Like we have different species even for the wheat, even for the paddy also. So what we are doing, we are trying to get the that variety-wise spectral measurements, and we try to develop a variety library of this that paddy or wheat existing in our field. So in this way, we develop a spectral library. Then we try to get a pure material pixel from your satellite image, and then based on this reflectance peak, absorption. I showed you the absorption, that dips are absorption or reflectance. In some cases, we are taking reflectance. Then we compare with the lab spectra, and then if we get all those things, then we go for the some algorithm like spectral angle mapper. That one of the algorithm maybe you will see in your um, software. What software you are using, by the way, for image processing right now?
Sir,
Yes.
ADAS.
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 Okay, so ADAS, do you have SAM classification tool? Because we are using either R or NV.
No, sir, we don't have, sir.
Okay, in SAM, spectral angle mapper. Uh,
No, sir.
Okay, okay. So NV is more stronger than you can say ADAS, because NV has this. I will show some of the more analysis that you will see that there is a SAM spectral angle mapper. Then there are other tools that through that you can build your spectral library. So once you have a spectral library ready, then you can go for a large scale analysis. So with the help of spectral angle mapper, what a spectral angle mapper do, that suppose you have a ground based spectra of wheat, then you have a satellite image. So you try to uh, uh, match the spectra in your satellite image with your ground, and then you will classify where you are having wheat. So in this way, if you are going for some minerals, it is doing like that. So this is the one of the that things that if you suppose you have 4 or 5 things over here like red brick, kaolinite, sandy loam, concrete, and grass. So if you see, if it's the spectral signature, all the spectral signature are different. Grass has different, kaolinite has different, red brick has different. So in this way, we have different spectral signature. So suppose you have a satellite image and you have a satellite image and you want to match this spectral signature. So what you will do, that you will match this spectral signature with your satellite image, and you cannot simply go and match with your eye. You need to have some algorithm, an algorithm which is actually doing spectral matching, not your what you can say what you are doing, AOI or ROI? AOI, I think, area of interest, like in ADAS. AOI. So in how you are creating your AOI, you are selecting some training pixels. So that training pixel is like it's not giving you any spectra, but it is giving you a reflectance based training site selection. But in spectral matching, you need a pixel, one pixel spectra, not 4, 5 or 10 pixels training data sets, reflectance based. So it is actually needed your more physical basis of measurement in a spectral angle mapper, and then it try to match the spectra, not the reflectance profile. So this way you will match the spectral angle mapper, and then you will get your that classification of an satellite image. So one of the important tool that we are using, that if you are going for more detailed analysis, like suppose you are getting a spectral profile, this is for a wheat crop, and see you can see a number of absorption areas, and actually these absorption area are either pigment specific or whatever biochemical parameter existing in leaves that is specific on that. So how we can check, or how we can know that uh, these absorption bands are actually responsible for which of the biochemical parameter. So what we need to do, we need to enhance these absorption areas. So that technique we call as continuum removal. That we call as continuum removal. So there are several absorption areas over here. See, you can see that there is a absorption area over here, here, here. So what we do, because it is one of the rigorous analysis that we do, we first enhance this region. So how we can enhance this region? We select the tangent of this area, select a line, and then it will zoom it, and then we take this spectra out. Similarly, we take this spectra out by continuum removal, this spectra out. Similarly, we take this spectra out. And once we have this spectra out, so this is this absorption must be happened because of some specific element in that object. So what we do, suppose we have chlorophyll, we have some other chemicals like carotene and phycocyanin, phycoerythrin in plant. In if we go with the mineral analysis, then you have calcium, magnesium, other type of. So we try to have that sample analyzed in our lab. We take this spectra, and then we try to correlate these bands with that spectra, that data taken. For example, if you have chlorophyll over here, chlorophyll value XYZ, some chlorophyll value here, and then you took this section out, okay, and now you have different, because each region has some wavelength, right? So suppose here you have 0.7. So we take this, suppose 0.7, it is 0.71, it is 0.73. So we take 0.71, 0.72 like this, and we try to correlate. So we try to correlate first with band 1, then we try to correlate with band 2. So the band which is giving the highest correlation is actually responsible for chlorophyll mapping, chlorophyll relation. So excuse me. Hello. Good morning, sir. Sir, actually talk चला रहा था, थोड़ी free हो जाऊँगा. ठीक है, अच्छा. Sorry. So कहाँ था मैं? हाँ. So if you see this spectrum, आप लोगों को समझ में आ रहा है ना? Complicated ज़्यादा नहीं हो रहा है ना?
हाँ जी सर. नहीं
यस सर, समझ में आ रहा है सर.
Oh, okay. So what I'm trying to say over here, that we take this absorption band over here, and we have several bands. So एक्चुअली लिखने का कुछ नहीं है मेरे पास अभी, इससे लिखने में दिक्कत होती है, इसलिए जनरली ऑफलाइन वर्कशॉप थोड़ी बेटर होती है कि आप थोड़ा सा इंटरेक्ट भी कर लेते हो, और कुछ प्रॉब्लम हो तो सीधा व्हाइट बोर्ड पे जा भी सकते हो. सो मैं यहाँ पे क्या कोशिश कर रहा हूँ समझाने की, सपोज वी हैव डिफरेंट बैंड्स ओवर हियर, लाइक बैंड 1, दिस इज योर बैंड 1, दिस इज योर बैंड 2, similarly band 3. So we write band 1, band 2, band 3, and then we have then we sorry. So we have band 1 over here, band 2, band 3, and then we have this chlorophyll. Suppose I'm taking a simple thing, chlorophyll over here. So chlorophyll values are here, x, y, z here. And then in band 1, what is your reflectance value at different sites? Suppose this is your satellite image, and this satellite image is formed not by only one image, one card. It is because it is a hyperspectral image, so you have a many bands over here, right? So each band is giving you one wavelength. So band 1 is giving, suppose blue is giving one wavelength, B2 red is giving one, green is giving one, and we have chlorophyll measurements. So we are having several test site, 1, 2, 3. We have several test site. So from each test site, you have, because it is a pixel, you have all these wavelengths. Test site 2, all you have all these wavelengths. Test site 3, all you are having all these wavelength. So because you are having all these wavelengths, you will get several bands over here, and then you have several chlorophyll over here. मतलब मैं ये कहना चाह रहा हूँ कि ये पूरा एक पिक्सेलेटेड इमेज है, पिक्सल है, तो हर पिक्सल में एक अपना इंफॉर्मेशन होगा. तो एक बैंड का इंफॉर्मेशन यहाँ आया, और यहाँ से ही हम लोग अपना क्लोरोफिल का भी प्लांट सैंपल भी कलेक्ट करते हैं. तो प्लांट सैंपल से हमने क्लोरोफिल निकाल लिया, तो यहाँ पे एक बैंड का वेवलेंथ भी मिला और यहाँ पे क्लोरोफिल भी मिला. सिमिलरली दूसरे बैंड, क्योंकि इसी के नीचे दूसरा बैंड है, तो उस बैंड 2 का भी हमें रिफ्लेक्टेंस मिला, और क्लोरोफिल तो हमने एक ही क्लोरोफिल सारे बैंड, क्योंकि ओवरलैपिंग एरिया है तो सारा एक ही क्लोरोफिल यहाँ पे होगा. सो यू हैव डिफरेंट क्लोरोफिल वैल्यूज ओवर हियर एंड डिफरेंट बैंड ओवर हियर, and then you need to do a correlation analysis over here. Simple. Suppose there are several other techniques available, but for sake of easiness, I'm telling that go for the correlation analysis. So whatever band is giving best correlation, you can use it for chlorophyll mapping. So this way, by enhancing this region, we can do. So by coming to more detailed analysis, that this absorption area that I enhanced in the previous slide, this in region I enhance over here. So you will see that by using this continuum removal, you are actually normalizing this absorption band. Initially, if you see, it is start from somehow 0.43 to 0.47, but once you enhance it, it will normalize from 0 to 1. See, it's normalized from 0 to 1. So what we are doing, we are trying to measure this depth and the absorption, just depth, absorption band depth and width. And because it is element specific or object specific, then we try to match this enhanced area to our satellite image. Then it is giving a much better prediction of things than your actual things that you are doing on your mapping, like you are selecting training pixels, then you are using maximum likelihood classification and all those things. But if you go with the spectra, it will give you much better information than using our training pixels. So here it is one of the things that generally we are taking in using one NV tool. In this we have continuum removal technique, but this graph is actually made from the Prism, another software that actually we use during our work. In that you can take this spectrum out, then you can calculate this continuum ratio, continuum slope, everything you can get measured, because it is automated software. It will give you all the values, and then you can go with the spectral matching. So here see, we are trying to do the spectral matching. We have observed from our ground, like the instrument that I showed you, we have instrument data, we have this scaled reference, then we have a satellite data. So up to you, if you want. Some people say that reference, we take hyperspectral radiometer with us as a reference and take observed satellite as a observed. Some people think that observed should be your and reference will be your satellite. So anyways, we need to match this spectra. So what we are doing, you cannot match two spectra like this. Suppose your reference and your observed. If you compare reference directly with observed, you will say, oh, there is no matching. It is, this absorption depth is very low. Here absorption depth is very high, so you cannot match. So basically we need to do the normalization. So you need to do this continuum removal of this your reference spectra as well as your satellite spectra. Then you can compare, otherwise not. It will give you false value. For example, suppose you are in the field and with the help of your ground radiometer, that gun I showed you, it is very sunny day. So what happened when you take the measurement, you will get very high reflectance value, right? Because of sun. But suppose a satellite is passing and that day sunlight is not that good, so you will get reflectance, but that reflectance will not be very high. Shape is same, shape will be same, but the value will not be same, right? मतलब मेरे कहने का मतलब ये है, सॉरी, मेरे कहने का मतलब ये है कि अगर आप एक थोड़ा सा कम लाइट कंडीशन में आप फोटोग्राफ लोगे अपनी फोटोग्राफ, और एक आप थोड़ी सी ब्राइट लाइट में जाके फोटोग्राफ लो, ऑब्जेक्ट सेम है, आप ही हो, लेकिन आप थोड़ी सी डार्क में लोगे तो फोटो की क्वालिटी थोड़ी सी डिम आएगी, आप ब्राइट सनलाइट में लोगे तो फोटो की क्वालिटी थोड़ी सी ज़्यादा ब्राइट आएगी। क्यों? क्योंकि आपके फेस से रिफ्लेक्टेंस ज़्यादा हो रहा है, लेकिन ऑब्जेक्ट सेम है। लेकिन आप कहोगे कि नहीं ये दोनों चीज़ें डिफरेंट है, बट दोनों चीज़ें डिफरेंट आप इसलिए नहीं बोल पाओ क्योंकि आप जानते हो कि फेस वही है तो चीज़ वही है। बट अगर आप कोई सैटेलाइट में पिक्सल देखने जा रहे हो तो वी कैन नॉट सी अ फेस, यू कैन सी ओनली अ स्पेक्ट्रा। सो स्पेक्ट्रा होता है कि उस दिन लाइट बहुत ज़्यादा हो तो रिफ्लेक्टेंस ज़्यादा मिल रहा है, उस दिन लाइट कम हो तो रिफ्लेक्टेंस कम मिल रहा है, लेकिन ऑब्जेक्ट सेम है। सो व्हाट इज द टेक्निक टू अवॉइड दोज टाइप ऑफ मिसमैच? So that we call as continuum removal technique. In that we trying to scale it. Okay. So what we are doing over here, we have observed, we have rescaled by using continuum removal technique. We rescaled this spectra. So that's why we are called scaled. And this is your object from your ground. So if you see, if you compare these two, you will get a very high correlation of about 0.94 because you now normalize it. But if you compare this object with your actual one, then you will not get very good match because these depths are not matching. But once you rescaled it, you balance the light and other thing, now you are having a good match with your observed one. So now that's why we are using this continuum removal technique before implementing in our satellite image. Otherwise, if you classification is very simple task, take a RY or AY and then classify your image, but that need not be very good because we are not doing any more in-depth analysis of those spectra. So after doing this, you can do an in-depth analysis and then you can go for a more detailed mapping of this, you can say, your object. So this is one of the examples that we are showing, that here is a dolomite and here is a calcite. What is the difference between this? That dolomite is having calcium magnesium carbonate and calcite is having only calcium carbonate. So it is CaCO3, it is CaMgCO3. If you see with the naked eyes, you will not differentiate it. But if you go with the spectra, you will see that these two are different. Their absorption peaks are changing. And these things generally we are using to differentiate two minerals in a satellite image. So what we do, we have a pure minerals spectra with us, and then we try to do this continuum removal, do reflectance matching, and then we run on the actual satellite image to get minerals over, on that area. Similarly, if you go with the gases, you will see that there is a difference between gases also. That CO2 and H2 both are having different curve. Then you can quantify CO2 in your atmosphere. You can also quantify water vapor. So here I'm taking some more detailed example that we did for some of our work. That here we are having calcite. We have having several other minerals like alunite, pyrophyllite, like this calcite. Maybe if some of you are from geology, you know all this. Otherwise, just take as A, B, C, D something. So if you see the calcite absorption band, it is generally coming over here, because if you do the absorption band enhancement, continuum removal, do the band matching, take the band reflectance and match with the calcite concentration. Calcite concentration you can take by using EPMA, electron probe microbe analysis. You can get quantity of calcite and match it where you are getting the highest correlation. So in this area, it is giving highest correlation with calcite. Similarly, but pyrophyllite in this area are getting. So you need to see the absorption band, then take the absorption band and then do the continuum removal and then do the reference spectra scaling and just try to calculate this fit value R square. So you see that we are taking several absorption areas. Okay, we try to fit with our lab based. This is your lab based spectra, and we try to fit. And you see, in all the cases, we are having highest correlation over here, 0.99. Okay, in this region. So this is the best mesh. So we need to use this area to classify our satellite image. Okay, so it is an exercise generally you can do in your research work. And once we have this spectra ready, then just implement on your satellite image. For example, here after all this analysis, this is one of the satellite image, Hyperion. Then we have chloride, calcite, dolomite, illite, gypsum, and colonite spectra signature. We try to enhance the area and then classify the satellite image. And you will see that it is mapped where you are getting muscovite, calcite, all these elements in the satellite image. So it is one of the tasks that is rigorous tasks that you need to do before going for the mineral exploration. Similarly, in our agriculture field, we have different crops here: cotton, chilies, rice, sugarcane, and you can see all the spectral signatures are very different. So with the help of this, generally we go for the spectral signature creation. Hello, सर एक टॉक सर चल रहा था मैं आपको कॉल करता हूँ. So yeah, okay, cotton, chilies, rice, and sugarcane. So you have different spectral signature ready over here. Then what we do, we have a satellite image of our Hyperion image of our area, and then we try to map because we have spectral signature taken by our radiometer, and we try to match where we are getting the similar type of spectral signature. Similarly, we can go for the chickpea, wheat, sorghum differentiation, depend on your objective. And here in our forest area, you can also go with the differentiation of even dry pine and dry grass. If you go in the forest area during the summer or autumn season, you can see that there are pine leaves on the ground. But before falling of pine leaves, there are grasses also. And if you see their shape, they are looking very similar, pine leaves and the dry grasses, because both are looking like needle-like. So how we can differentiate dry grass with the dry pine or with the rangeland? So here we plotted the different graphs, then we did a continuum removal over here. Okay, and then when we enhance these regions like this, scaled it, and we see that with the rangeland and dry grass, it is giving a high match instead of pine. So that area is actually a rangeland, not a pine. So you can differentiate all those with the help of spectral things obtained from the area. So what is the basic procedure of doing all this analysis? It is very simple. I've been giving you a layout of NV software. Sorry, I didn't know that you are learning on DAS. So what we are doing here, that this is a Hyperion image, one of the satellite image available, and for past years. Now it is decommissioned. It is now because of fuel and technical issues, it is now decommissioned. It is now not providing any data now, but past data you can use it. So Hyperion, and then we have L1 reflectance data. We have pre-processed it. We are doing atmospheric correction. Okay, atmospheric correction is there. So we are doing atmospheric correction using one software we called Flash, and then we do geometric correction, shape matching, and then minimum noise fraction to reduce the noise in the satellite images. Then we try to get up pure pixels. Then we see different ways like visualizer, whether those pure pixels are actually pure or not. For example, सपोज इन योर, आप लोगों ने क्लासिफिकेशन कुछ किया कि एक भी टास्क कुछ क्लासिफिकेशन का हुआ आप लोगों का?
नहीं सर, अभी नहीं हुआ सर।
अच्छा, क्लासिफिकेशन अभी नहीं हुआ है, अच्छा। सो आप लोग जब क्लासिफिकेशन का टास्क करोगे तो शायद आप लोगों को एक एओआई सेलेक्ट करने को मिलेगा एडास में। तो उस एओआई में क्या होता है, आप लोगों को पिक्सल सेलेक्ट करने होते हैं। फॉर एग्जांपल वाटर के पिक्सल सेलेक्ट करने होंगे। सो गलती से अगर वाटर के पिक्सल को सेलेक्ट करने में आपने कोई वेजिटेशन का पिक्सल सेलेक्ट कर लिया और फिर उसी ट्रेनिंग को आपने यूज कर लिया क्लासिफिकेशन में, तो वो वन वाटर जो वन वेजिटेशन पिक्सल आपने सेलेक्ट किया, इट विल गिव यू सम एरर इन क्लासिफिकेशन। सो प्योर पिक्सल सेलेक्ट करना, इट्स वेरी टीडियस वर्क and you should do very carefully. So once we have this pure pixel index, here we do the ND visualizer. We try to see the different angle whether any other pixels are in that ROI or AOI or not. If any other pixels are there, then we again select all those things. Then we go with the end member like your uh, pure pixel, best pure pixels export, and then we go for any classification, maybe SAM, or maybe you can go with the mixture tuned analysis. There are many algorithms available, but SAM is more easy and easy to use. And then we can go with the mineralogical mapping or any other mapping that you want. But this thing is common for all those analysis. Okay, so here we are using some geological map also, previously developed geological map, because what happened, we are doing mapping with the satellite image. But previously, if you see Geological Survey of India or USGS, they all do field-based survey also. So you can match also that for better error analysis. So when it is matching in a good way, then you can say, okay, my technique is good, I can go for other areas also. So validation is very important in this type of work. Okay, so coming back to atmospheric correction, why we need to do this atmospheric correction? Because with the microwave satellite, what is the advantage? That they are transparent to atmosphere. Means if there is a cloud, aerosol, dust, microwave signals can easily pass because they are not, they can penetrate through those things. But optical infrared cannot. If there is a cloud, you will, for example, अगर आप फोटो खींच रहे हो अपनी कहीं पर अपने कैमरे से और बीच में डस्ट वस्ट आ गया, आप खींचोगे तो आपकी फोटो क्लियर नहीं आएगी। और शायद इसीलिए आप लोग जब आप कहीं फोटो देना होता है कहीं पे प्रिंट होने के लिए, तो क्या होता है कि आप स्टूडियो में खिंचवाते हो फोटो। स्टूडियो में क्या करता है कि फोटो आपका लिया, आपको फोटो लेने के बाद फिर आपको फोटो की क्लीनिंग करते हैं वो लोग, सारा उसमें से नॉइज वगैरह हटाते हैं, तो यू लुक वेरी गुड। जैसे मैट्रिमोनियल्स की जो फोटोज होती हैं तो उसमें वो लोग क्या करते हैं कि आपकी फोटो एकदम फोटोशॉप करके अच्छी से बना के देते हैं। व्हाट दे आर डूइंग ऑल रिमूविंग ऑल दोज नॉइजेस, ऑल दोज डस्ट एंड एवरीथिंग ड्यूरिंग योर फोटो सेशन। सो वो फोटो सबसे प्रोफेशनली तैयार करते हैं। सेम वे क्या होता है कि वो आपका जो कैमरा है ऑप्टिकल कैमरा है, तो ऑप्टिकल कैमरा आर जनरली सेंसिटिव टू दोज नॉइजेस, डस्ट और जो भी है। बट सिमिलरली थिंग जो हमारा सेटेलाइट ऑप्टिकल सेटेलाइट है, लैंडसैट, ये सब हाइपरस्पेक्ट्रल, ये भी ऑप्टिकल है, ऑप्टिकल इंफ्रारेड, तो ये भी डस्ट और इन सब से काफ़ी सेंसिटिव होता है। अगर बीच में डस्ट की लेयर आ गई, क्लाउड की लेयर आ गई, तो इमेजिंग डिस्टर्ब हो जाएगी, आपको नॉइज मिलेगा। और क्लाउड आ गया तो पेनिट्रेट नहीं कर सकता ऑप्टिकल, सो यू विल नॉट गेट अ, you will get a shadow, black patch near below that area, below that cloud, because that optical cannot pass. So there are several issues. So we cannot, there are techniques to remove those clouds, resampling, all those techniques. But instead of cloud, if you have water vapor, aerosol, ozone, these are the three elements that are actually creating noise in your satellite data sets. Optical infrared satellite data sets, ozone, water vapor, and third one is aerosol. So how we can remove the impact of those? So for example, if you have a water vapor emissivity and absorption is already known, because in lab you put water vapor, you pass a signal, how much it is absorbing, how much it is getting out, you know. So absorption, emissivity, you can easily quantify of water vapor, ozone, or some of the aerosols. So when light is coming from the sun, hitting that those aerosol particle and then going up to the satellite, then you can quantify how much scattering happened with that particular water vapor or aerosol, because in lab condition you know how it is scattering your satellite. So suppose 1 unit of radiation or wavelength is coming and hitting that aerosol or water vapor ozone particle, and 0.7 is going towards your object and 0.3 is scattered. So how we can calculate this 0.3? So this algorithm flash is actually calculating the amount that is actually scattered by that water vapor, ozone or aerosol, and then we add that much of scattering into your original signal to make it equal. For example, 0.3 is lost, so how we can calculate this 0.3? So by using this model, you can calculate how much is lost. So once you have the lost figure, then you add in your actual signal, then you will get a total reflectance. So this way, this correction is very necessary. So for example, how we can do this? We have this latitude, longitude. Okay, we have sensor altitude already known. For example, this is this sensor altitude is giving for suppose your space-borne satellite. Like some of the sensors are 36,000 kilometer above Earth's surface. Some are near to Earth's surface. So these are all fixed. If you um, open the lens at 8, download this image, then you will get a metadata file also. In that metadata file, just open it. You will see the sensor altitude. You will see the pixel sizes. You can see the flight date when that satellite pass over the object. Latitude, longitude, you can check. Then put all these figures in. क्योंकि क्या होता है कि सपोज इफ यू नो द डेट ऑफ फ्लाइट, देन यू नो दैट कि ये मानसून सीजन का फ्लाइट है और इंडिया के ऊपर से पास किया तो देयर इज हाई चांस कि इस दिन थोड़ा सा वेदर गड़बड़ होगा. सपोज अगर समर के टाइम का है तो समर के टाइम में क्या होता है कि सन अर्थ डिस्टेंस ऑलरेडी नोन है, क्योंकि ऑर्बिट फिक्स है सन का अर्थ का. तो यू कैन नो कि इस दिन पे हमारा अर्थ सन से कितनी दूरी पे होगा. So you can have that distance. So once you have that distance, then you can see कि अर्थ से कितना, सन से कितना इलेक्ट्रोमैग्नेटिक वेव्स आ रहा होगा, कितना एल्बिडो क्रिएट हो रहा होगा. So reflectance profile you can calculate. So all this astronomical or physical things are already put in this model. So you don't have to go with all those things, because what you have to put here, you have to put here your visibility on that day, because this visibility is dependent on your water vapor and aerosol condition. So if you go with your nearest what you call airport, they are providing this data set, or you can Google it. You will get that visibility information of your area. Then put that figure in, and then you can see different modeling aspect. Like we are in tropical country, so we put tropical model. If you are in UK or Europe, then put temperate model. And then because we are calculating noise in the ionosphere, don't create much noise. Troposphere is having highest amount of water vapor, ozone and aerosol, so we are using this this tropospheric model. And then we put all this figure in flight time, and then you apply, and then you run it, you will correct your satellite image and give you the actual image. So it is very easy. Okay, so but if you go with the algorithm, it is quite complicated, but you don't have to go if you don't want to improve this tool. If you want to improve this tool, then go dig that algorithm and improve it. That will be a good work, because there are only default option available. For example, you want to go with the maritime model is not here. Suppose you are going to work with the ocean region, like coastal region, then maritime model is not available. And maritime area, you will see that they have sea and land both effects there. So if you want to improve this, then you go with the code and everything. If you don't want to improve, then put your figures in and get your reflectance data, actual reflectance data, noise removed. So in this, I already explained that pixel purity index are there. You can use this multispectral and as well as hyperspectral. You need to find that pure pixels. You should not go for with any noisy pixel in your selection. If you have one noisy pixel, it will disturb your whole classification. Then after doing this PPI, pixel purity index, then we go with the scatter plot to see if there are other pixels coming in that or not. So if you plot the scatter plot, Suppose you are having the water, so water reflectance is range is fixed, but you are seeing that some of the pixels are not in that range. If you plot that, then it means those are the bad selection. So you need to relook into your pixel purity index, extreme pixels, and remove all those pixels. So you can do in this tool also that you can directly remove from your window these pixels, those noisy pixels, and then you will get the best pixel purity index. And then after that you go with the end member, like extraction of those data sets, and then do classification by using any tool. Here we are also having some principal component analysis to reduce those noises. For example, principal component analysis, like it is a data redundancy technique. So in data redundancy technique, what we do, suppose we have a जैसे कि मान लो आप लोग कहीं जा रहे हो कोई शॉपिंग करने, और you are buying some stuff, like you are going to buy shirt, suppose. So you will not buy three blue shirt, because that is not unique. All the three shades of blue giving a mostly similar information. Similar thing happened with the bands also. Suppose you have 400 bands, and you want to run 400 bands in your computer, then it will hang your computer, because file size is very high in GBs, and when algorithm is running, it will consume most of your processing nodes. So it will slow down your computer. So what we do, we have to do principal component analysis. We try to reduce the redundant data. So suppose you have a 1 to 400 bands, and 3, 4, 5 bands are having very close match, because those are the shades of blue. So suppose band 2 is 0.91 band. If you see band 2 correlation with band 3, it is giving 0.99. Band 3 with band 2, it is also giving 0.999. So those are very similar type of bands. So you can remove 2 bands and go with the only one. So PCO do those things for you. It remove the highly correlated bands and give you fewer bands, so that you will have the unique bands with you for your classification, for your spectra creation. So in this way we are going with the PCA technique. And minimum noise fraction already told, we try to remove those noises by using this type of technique. It also find out, PC also find you some of the very unique in the sense, because of very noisy data set, they are very unique. So you can also check and remove those bands. For example, sometimes because of band 1, band 2 channels are getting contaminated because of water vapor and all those things. So you will get a black and white, totally black and white image. So you can remove this. It's like a pixelated salt and pepper effect type of thing. So you can remove those bands. So this way you can check and remove, and then you can go for your classification. So this is SAM that I'm telling about, that it tried to find this angle between the two materials and try to match. Once it is matched, then you can classify. This is a crop classification with varieties that I told, that we can go with the varieties. So there are several variety of rice here, sugarcane here, cotton here, chilies here. So we try to get the spectra of all the varieties. Then we do some removal technique, and then we implemented this, and then you get this map of an area. It is Hyperion image, and you can get distribution of those varieties in the image. Similarly, in agriculture area, you can take different discrimination, like crop type discrimination. You can also go with the disease and stress assessment. Like here, if you see that there are 2 crops, and some of the crops are diseased. So even you can go with the healthy and diseased differentiation with the help of this hyperspectral, which is not possible using the multispectral. So you can see that you can easily differentiate all those area where you are getting low signatures absorption band, and when you compare, you can see that in a diseased one we have a very high drop of chlorophyll values, but in healthy we have very good chlorophyll values. So you can differentiate disease and healthy also. Urban mapping, it is quite at high level we are doing this urban mapping. and you can do high resolution mapping of urban areas also. Even you can see what type of urban cover is there. It is a rural type of covering, earth, rural type of roof is there, or concrete roof is there. You can differentiate. Similarly, you can go for the pigments mapping in your ocean or water monitoring. Like here, you have different depth for chlorophyll, then all these parameters. Then you can monitor by using this hyperspectral. Let's see here, quality is different. Here, quality is different. You can monitor. Similarly, vegetation mapping is there. Soil mapping, iron in soil. Iron is very important. So you can do ferrous and ferric differentiation. Here, at this point, you will get a ferrous and ferric differentiation. So you need to enhance this region to quantify iron in the soil. So you can also point some of the heavy metals. Even with the snow and this other areas you can do. Then this we did for our phenology, crop phenology, that we try to see how this spectra is getting changed with the crop growth. So when crop is growing up, then when first node is there, then when head is visible, then rooting, flowering. So all these things you can map, you can see. And if you have a large satellite image with you, you run all these signatures and you will see that what is the stage of your crop in a large area. So, and if you quantify stress also, diseases also, then you can help in crop management also. Similarly, this is one of the forestry work that we are talking about. Sorry. This is the forestry work we are talking about, that we are having different species spectral signatures with us. And then we did the continuum removal of all this spectra, and then we put in a Hyperion and classify that Sariska forest into different for all these species. So you can do by this, and then you can see how much the percentage of all these crops in a particular area. Okay. This is one of the book that we did previously. Thank you. I hope it is. I finished well in the time.
Anji sir, no issue sir. Sir, any question? Participants?
Time is 10 to 11:30, right?
Yeah, yeah.
Book name slide again, sir.
Anji?
That book name की slide जो है ना sir, second last slide, book वाली.
Ha.
Yes, sir.
So, if you have any question or any query or anything, please ask. I will be happy to.
Yeah, please. Participants?
Sir,
Sir, I have a question.
Yes.
One by one.
Please, please tell
Sir,
your
हमारे
name
पास
and
है.
also please tell your name
ladies
and
first,
also your
go ahead,
background.
please.
सर हमारे साथ है कोई नहीं, अब सर है, आराम से एक एक करके पूछो.
हाँ, कोई दिक्कत नहीं है.
Sir, can we have access to hyperspectral data from open source?
Yes. As I told that, if you can you tell me about your background and some of the information?
Sir, I am pursuing MSc Geoinformatics.
Okay. So MSc Geoinformatics. So why I'm asking, because if you're a PhD student, then it's like if you want to work on past data sets, then Hyperion is available. Hyperion we call as. So that data set is available, and other data set, if you want for a recent years, then Prisma is available. Prisma, Prisma.
Okay.
Prisma is available. So you can use both the data set for building a long-term analysis or doing a long-term change analysis and all those things.
Okay. Thank you so much, sir.
Yeah, next question. Next, Sunil.
Yeah, sir. Hello, Prashant sir. My name is Sunil. I am pursuing my MTech from under the guidance of Suraj sir.
Okay.
Sir, I have a question related to image classification. As you mentioned, it is very hectic work to specify differentiate the classification between the cells. We need to be very careful while selecting.
Yes, yes.
Yeah. So isn't it there are chances for the errors, sir? So is there any automatic process which can be differentiate between the cells and it will automatically detect the classification?
Actually, there are tools, but what happened? Tesla launched automatic car, right?
Right.
So, but there are high chance of accident because that is algorithm based, right? And if there is some emergency response or something, that software may fails, right? That's why it is not very popular and car is not yet fully launched. So there are several tools for automatic classification also available, like with different software. But what happened? Suppose there is a pixel, right? And in one pixel, 30 by 30 meter pixel, and in that pixel there is a vegetation and urban area. Both are there because 30 meter by 30 meter is a big pixel size, right? You can
Yes.
have a small garden as well as your house. So if that algorithm come to that pixel, what will be his decision? Urban or garden?
So we can see that by manual interpretation only, sir.
Manual interpretation or in algorithm, you have to improve those things that if building area is more than 60%, then classify as building. Or if garden area is more than 65%, classify as you can say garden.
Garden.
Okay. So that way things happen. So, but what is the problem that if you see the 30 meter by 30 meter pixel, you will see an average value of garden and building.
Yes.
For example, pixel reflectance is 0.3. Now tell me how much percentage is from building and how much percentage of reflectance from garden. You don't know.
Yes,
So those are the complications that algorithm faces.
yes.
So that's why we are not getting 100% accuracy.
Yeah, when we go for the lower resolution, higher resolution images, then this work again becomes very hectic.
High resolution is like if you go with 1 meter Iconos or like 12 meter Sentinel, then you can have you can solve up to some extent those problems. But if you go with a multispectral like Landsat, what generally we do, we try to see the area, go to the ground. Suppose in area you are there and it has both building and plants, right? And we try to see how much percentage is the building and how much percentage is the ground. Okay, means open air area, and then we try to get the pixel value of that area. Similarly, we go to some other area, we try to see if building area is high and garden areas come, we try to get that percentage. And similarly, in third case, we have high garden area and low building area, and we try to see the pixel values. So now we have the pixel values reflectance over there. Now put in your algorithm that in high building area and garden, this much is the pixel average pixel value. So put that value in, then it will help you in improving your classification accuracy.
Okay, sir. Thank you.
Next, please. Next question.
Yes, sir. I have a question.
First Raghu, then Mujahid.
Okay, thank you, sir.
Sir, is cloud cover an issue with the hyperspectral images like we face in multispectral images?
Issue means what type of issue?
Sir, cloud cover.
Yes. Both are optical and infrared. Multispectral we have. I think Raghu, can you switch off your mic, please? Okay, so what I'm trying to say that both multispectral and hyperspectral are different because of number of bands, right? Both are optical and infrared. So both are contaminated with this cloud cover. Both cannot penetrate.
Okay, sir. Thank you, sir.
Sir. No?
Mujahid, please.
Yes, sir. Yes, sir. As you told, the Prisma data for the hyperspectral, is that data have the Z value also?
The data has
Z value. Height. Height, sir. Height. Z value. Elevation value.
No. That is not a topographical data sets. DM generally have Z values, those data sets. That's why you are getting elevation maps and all those things like SRTM and all those things, because they are generally having twin satellites to measure the top and bottom of the scene. But this hyperspectral optical, they are using the pixels. They are not going with the multi-angular observations. That's why you don't have the Z values.
Okay. Thank you, sir. I
You
just
cannot use hyperspectral to create DEM. Okay.
Sir, for the minute elevation or Z value, which data you will suggest for me, sir? I'm pursuing
You
PhD
can
in
go
this.
for the LOS2, that is also providing a very high resolution DM. You can go for SRTM. You can go for Cartosat. Cartosat is Indian version, Indian
Yes, sir.
satellite data set. You can download from Bhuvan. SRTM you can download from Earth Explorer. LOS2 you need to see. I think it is distributed through JAXA, so check that also. Maybe scene is available for your site, maybe not. But SRTM is available for whole globe. Cartosat is available for India region. Okay.
Okay, sir. Okay, thank you, sir.
So there is another question coming up that says ki how hyperspectral remote sensing will be used for flood mapping and forecasting.
Flood mapping, if you want to flood mapping, you can do with the multispectral also. You don't have to go with the hyperspectral, because in flood, if you see the pixel value of water and pixel value of land, both are very different. So you can easily differentiate flood area with Landsat images, and Landsat images available every 16 days. So you can go with the flood modeling, recession, and as well as you can go for the forecasting also. Hyperion data set, if you want to see the water quality of that flood water, then you can use. Of course, you can do the flood thing, but you don't have to do that rigorous exercise to see the flood. If you want to see the water quality or changes in water due to flood, then you can go with the hyperspectral. Otherwise, map with the multispectral. Don't go with the high size hyperspectral data sets, because volume is quite high.
Okay. Sir, there is another question from the students that how this data will be used for forest biomass studies.
Okay, so forest biomass is actually, you can see that we are using Landsat also, right? With the Landsat, we have allometric equation, and we put those allometric equation to get this biomass. Allometric means it is based on NDVI, LAI, and then you can get this biomass. But most of the previous algorithm that we are using with Landsat or other multispectral satellite, that they are considering biomass irrespective of vegetation cover, type of vegetation cover. With hyperspectral, you have all those data set like NDVI, and you can also do LAI calculation, as well as you can go over the species type mapping also. So once we have the species type mapping, then you can better say that, okay, it's a oak forest, this is a pine forest, biomass of this pine forest is this much, biomass of this oak forest is this much. But if you go with the multispectral, you will say that biomass of this forest is this much. You cannot go with a specific species type of thing. So generally in economical tree species that we call, we need to say that कौन सी स्पीशीज ज़्यादा कम हो रही है, कौन सी स्पीशीज ज़्यादा बढ़ रही है, किसका बायोमास घट रहा है, किसका बायोमास बढ़ रहा है. So all this thing we need to say. So हम लोगों को ज़्यादा हाइपरस्पेक्ट्रल की स्पीशीज लेवल पे भी जाना पड़ता है, प्लस बायोमास से मेजर करते हैं. तो एक ही हाइपरस्पेक्ट्रल से आपको तीनों काम हो जाएगा, बायोमास भी हो जाएगा, स्पीशीज भी हो जाएगा, प्लस आप बाकी इंडाइसेस जो कैलकुलेट करते हो मल्टीस्पेक्ट्रल से, उससे 1000 इंडाइसेस आपको ज़्यादा मिलेंगे हाइपरस्पेक्ट्रल में.
So there is a last question that I'll be taking from the students, that
Please
how
tell me.
hyperspectral remote sensing is used for mineral exploration and coal minings and its advantages.
As I told or shown in my one slide, that multispectral don't have those absorption bands. If you see that one aspect I showed, that in Landsat you have a flat line, means it don't have any measurement in that area. But if you go with the hyperspectral, we have measurement in that area also. So suppose in coal mine, if you want to go with the mineral mapping, suppose iron hematite, or you want to see either it is hematite or it's a magnetite. One is ferrous, one is ferric, like Fe2O3 and Fe3O4. So we can differentiate iron 2 plus and iron 3 plus also, because color is changing. So once we have the hyperspectral measurement, if you see the iron 2 plus iron 3 plus absorption area, you will see that there is a difference, and you can see that in that area magnetite is high, in that area hematite is high. Even you go with the more minerals also, but in coal mines, or generally we go for the type of coals. You can do type of coals also, whether it is a bituminous or whether it is some other type of coal. So you can also do that with the, because all coal type are different signatures in hyperspectral.
Okay. Sir, and last question, because they said, ki, sir, can it be used for LST mapping?
LST again, I tell you that LST algorithm is already well established. Means if you go with the most of the LST algorithm, what they do, they need a thermal band, right? So you have thermal band available with your Landsat 8. You have thermal band available with LIS also. So you can, I think this thermal band is not there, but Landsat 8, Landsat series has thermal band. So what you need to do, you need thermal band, you need plant fraction. And plant fraction you can calculate with the help of NDVI, LAI. Put this, get your emissivity, and then multiply with a coefficient that is given in your Sobrino et al. Paper, and you will get LST. So for LST, you don't have to go with the hyperspectral, because hyperspectral generally it is up to short wave infrared, but they don't have any thermal band in hyperspectral. I told you optical infrared. I haven't mentioned it is optical infrared or thermal. Thermal is available only with Landsat and other Sentinel series, not with the hyperspectral.
If I've left any of the questions, still you can ask, as I've taken majority. Still, if I've missed any question.
Yeah, thank you, sir. This is Varun this side, sir. Thank you very
Okay,
much.
Varun, yes, please tell me.
Sir, it was very informative, sir. I have only one question, that there is a data constraint for hyperspectral, basically. So,
Actually, previously there was a data constraint, but last year only Prisma is launched. So we have a data supply for hyperspectral also. Previously, after Hyper-N, there is a gap of 1 or 2 years for this hyperspectral data sets. But now it is solved. Prisma is there, and we have Prisma data sets also in one of our work, and it is quite good. You can use it.
so we can.
And average NG 2024, average NG will be launched before 25. So
Okay,
there will be no problem.
Can we get this Prisma data free of cost?
Yes, it's free of cost. Free of cost, and you need to sign a form with them.
Okay.
Because more like Landsat, you have to make an account and then you can download.
Okay, sir. Actually, previously in my work as in JNU, I have worked on Hyperion, but after that, I didn't get any data.
Hyperion frequency is also not that good. If you get the temporal coverage, is not that good over a same area, but Prisma temporal coverage is quite good.
Okay.
So you can go with a Prisma, and GISat is going to launch. So GISat 2 actually is going to launch. So that is also having a hyperspectral measurement. So you will have data sets. Prisma you can use right now. It is good data set. Bands are also good, and we have used that data set. Is giving quite good result with our soil nutrients mapping.
Okay, thank you very much, sir. Thanks a lot for such an informative session on hyperspectral remote sensing and its application.
Thank you very so much.
Any questions still that anyone wants to have? Don't be scared. Don't be scared. Rishabh?
Yes, sir. Good morning, sir. Myself, Rishabh Singh. I'm pursuing MSc Geoinformatics from Gyan Bihar University. I have one question, sir. Sir, what is the major difference between hyperspectral data and multispectral data? Because whenever we talk about Landsat data, so also have a 11 band, so why we cannot, sir?
Okay, Rishabh, I can, like in our first slide, I showed that multispectral has only 12 to 30 bands, right? And hyperspectral, we have more than 300 bands, 200 bands like this. So, like, जैसे तुम्हारे पास 3 कलर है RGB, तो R एक वेवलेंथ में मेजर किया, R का मान लो तुम्हारा 700 नैनोमीटर के आसपास रहा, और ग्रीन तुम्हारा 500 नैनोमीटर के आसपास रहा, ठीक है? पर ग्रीन और रेड के बीच का इंफॉर्मेशन तुम्हारे पास कोई नहीं है, है ना? So because we don't have any bands or filters in satellite to measure those regions, So that why that those data sets are discrete. Multispectral data set are discrete because we have only information for a particular region, but we don't have any information in between that. Like green and red के बीच में कोई information नहीं है. But in hyperspectral we have continuous bands. Even after green there are several nanometer bands are there, so it's giving a continuous array of information. So that data gaps are now covered in hyperspectral. So if you have something in between that region, you can map also. That's why multispectral we call as discrete and hyperspectral we call as continuous.
Yes. Okay. Thank you. Thank you.
Hope that all questions are answered. This is my last. Okay. There is no question coming up. So, sir, with this, I will take this privilege on behalf of Center for Climate Change and Water Research, Suresh Gyan Vihari University, Jaipur, Rajasthan. From my heart of my soul, I sincerely thank you that from your busy schedule, you have enlightened us with the latest technique of hyperspectral remote sensing, where we were very fortunate, where you highlighted the applications of how Hyperion data has and hyperspectral data has got a advantage over multispectral data sets. Uh, uh, we were trained on SAM model. Otherwise, we were also trained with pure pixel index. Many of the new terms, they were new to us too, and we like that in near future also you will be blessing our student, our university, and in near future we can have some collaborative research papers, and research students can go for their masters or PhD guidance under your supervision. And if you allow, we will have a further collaboration.
Sure,
So
sure,
thanks a
sure,
lot.
definitely. And it is really nice for me also to interact with your students as well as giving a talk in this workshop. So I really like that students are really interested and they are asking questions and they're trying to clear their doubt. So it is good. You have a very good participant in this workshop, and
Yes.
I really think that they will learn a lot from your workshop. So all the best, and I hope if they have any question, they will write to me directly also. Please provide my email so that I can,
Yes.
if they have any question, they can ask. And of course, if they want to do some work, they are always welcome to my lab.
So thank you, Dr. Shruti here. Thank you very much for such an informative and descriptive session on hyperspectral data uses, various software, how they can use, even we can use. So, sir, in future we will try to incorporate these things into our project, and we will seek your guidance, me as well as my students. Thank you, sir.
Definitely, madam. Definitely, madam. Thank you for inviting me.
Thank you, sir.
And we will see you soon someday when this corona is over.
Yes, sure,
And
sir.
sir, you are welcome in Jaipur. We are eagerly waiting
Definitely.
for your visit in our university, Jaipur Jagatpura. Our student at my university are waiting for your visit.
Definitely, I will visit. And let's see this. If corona is over, I will definitely come over there.
Yeah, sir. Thanks a lot, sir.
Thank you so much. Thank you so much.
Thank you, sir. Namaste.
Thank you.
Namaste.
Thank you very much, sir. Thanks a lot, sir.
Thank you, Varun.
Namaste, sir. Pranam.
नमस्ते
Thank you, sir.
अभी मैं लॉग आउट कर लूं मैडम
हाँ जी सर प्लीज
ओके बाय
तो सेशन अच्छा लगा
यस सर
Yes,
अच्छा धन्यवाद
अरे आधा क्वेश्चन तो तुम लोग का मैंने खुद से बना के पूछा भाई
Yes, sir.
तुम लोग पूछना चाहिए तुम तो ऋषभ यार तुम बीच में ही भूल गए कि पूछना क्या है बताओ उनको समझना पड़ा कि पूछना क्या चाह रहा है इंटरप्रिटेशन लगाया उन्होंने तो एक्सप्रेसिव होना चाहिए ना इसलिए मैं बोलता हूँ कि देखो बाकी पढ़ाई अपनी जगह एक्सप्रेस करना अपनी जगह
Yes, sir.
है ना तो वो बड़ा जरूरी है नहीं तो बहुत बार क्या है कि तुमको पूछना क्या है फिर तुम बीच में ही कंफ्यूज हो जाओगे तो अब 5 मिनट रेस्ट ले कि नेक्स्ट सेशन चालू करें 5 मिनट रेस्ट ले लेते हैं तब तक हम गपशप मार रहे हैं थोड़े मेरे जो स्पीकर है थोड़ा वो अपना रेडी कर लें रेडी हैं डॉक्टर वरुण?
Yes, sir, I'm ready, sir.
ओके, तो नाउ आई मस्ट रुको, तुम्हारा ये मैं बायोग्राफी बताऊं कि
It
ऐसे
was
तो
already discussed, sir. No problem.
तो already it has been discussed yesterday, and on the public demand again we have called our eminent speaker from Center for Land Resource Management, Dr. Varun Narayan Mishra.
Okay.
Land Resource, no, sorry, this is my older
Center for-
organization where I was
Oh,
working in Central.
You remembered your old organization.
That was in Central University of Jharkhand. So because I started my career, so always it by default it is just like whenever you're installing a software, it goes to a C drive. In the same way, whenever my first impression is always for land. So I'm very sorry for that. And on behalf of Center for Climate Change and Water Research, I again invite Dr. Varun Narayan Mishra to enlighten us with his thoughts and knowledge on elements of visual interpretation. With this, I hand over session to Dr. Varun Narayan Mishra.
Okay, thank you very much, sir. Thanks a lot for giving me the opportunity to again interact with the participants who are there in the workshop. And a very good morning to all of you. I hope my screen is visible now.
Yes, sir. Yes.
Yeah. So till now we have discussed about yesterday, as I have discussed about the process of remote sensing technique, and today Prashant Srivastav sir has already discussed about hyperspectral remote sensing and its application. But when we get the image, or when we get any multispectral or hyperspectral or any kind of image, so it is very important to interpret our images to get some kind of information. Means when we talk about image interpretation is generally a kind of information extraction from the satellite image. Whatever the image we are having, we have to extract some information from the satellite image, whether it is hyperspectral image or multispectral image, or you can say microwave images. So today I'm going to discuss about some basic concepts about the image interpretation of different satellite images. Okay, so I'm going to start with the term that is image interpretation. You have heard the word many times, image interpretation. Okay, so these are some of the common definitions, or you can say these are the explanations of image interpretation. It's examining of your images to identify the objects and judge their significance. Okay, the aim of image interpretation is not only to identify the objects, but also we have to judge, or we have to also examine the significance of that feature in our study area. And when we are going for image interpretation, it's a kind of information extraction. Without any information, no images can be used for any further application. Okay, so the main objective, or you can say the main aim of image interpretation, is to extract some useful information from the satellite images. Okay, and the interpreter, like we are the user, we use the satellite images provided by different sensors. So as an interpreter, we should be a specialist. We should be trained to study the photographs, or the aerial photographs, digital images, or any kind of images for different applications in different disciplines. Okay, and as we know that we are having different sources of images. We can get the spaceborne images from spaceborne sensors. We can have aerial photographs. We can have microwave images. So all the optical images, what we call it as a passive remote sensing, they generally based on the electromagnetic energy. As I have already discussed that the process of the remote sensing process, the use of electromagnetic energy or electromagnetic radiation. Okay, so whatever the energy is there is a kind of electromagnetic energy. Remote sensing images are generally a kind of energy of electromagnetic radiation captured by the sensor. Okay, and that energy will be used to detect and measure the target characteristics. Depending on the reflectance pattern, depending on the energy which is received by the sensor, is used to detect and measure the target, or you can say the characteristics of different land surface features. And image interpretation also involves a considerable amount of subjective judgment. Means we have to be very identify and to locate or to measure the characteristics of different images. Okay, And sometimes we need to be generalized, means our mind should be generalized. Our mind should be able to generalize the things to get the exact information from the images. And sometimes because of the complexities, or you can say sometimes if we are not able to identify the objects accurately, so it can also make some complexities in the image interpretation. So we should try to make the process easy so that we can easily identify different features, we can easily identify different objects in the satellite images. Okay. And as we know that all the digital images acquired from different sensors is a kind of pictorial representation of an object or landscape over the Earth surface. And images may be analog or digital, as we already know that if we are using hard paper map, it's a kind of analog images. And most of the remote sensing sensors we use to get the images in the digital format. So images can be provided in the analog format or digital format. Aerial photographs, whatever the hard copy of the aerial photographs we get, it's generally analog format. And most of the cases that the satellite images, different sensors are providing the images or data in the digital format. And each and every image, when we talk about the digital image is made of very small rectangular area that we call it as a pixel. Pixel is the smallest picture element of any image. Okay, pixel may be of different sizes depending on the spatial resolution of the sensor data. And each pixel is associated with a certain value that we call it as a digital number value or pixel value. We can also call it as a brightness value. Okay, so depending on the pixel value, we are able to identify the object. Certain pixel having high value, certain pixel is having low value. So depending on its reflectance pattern, sometimes we are having high pixel values, low pixel values. Okay, so pixel values are very important. On the basis of the pixel values or the variation in the pixel values, we are able to identify, we are able to detect different features. Okay, generally the sensor captures the images in the form of some reflected energy, and through some processing on the ground station, we convert the energy which is received by the sensor in the form of digital images that will have some kind of pixel values or pixel numbers or digital numbers. In short, we call it as a DN number, DN values. Okay, there may be various names. Brightness values can also be there, can be used for the pixel values. Okay. So now what are the advantages of satellite images or the aerial photographs over the ground survey, traditional ground survey, or when we go for the data collection in the ground through some field visit? So with the development of satellite remote sensing, with the development of aerial photography, we are able to have the synoptic coverage of that area, and that is not dependent on the time. We can get the images in any time, in any weather condition, and all the digital images acquired by the sensors, different remote sensing sensors are having a permanent record, and we can have the option to get the images in different bands that we call it as a spectral resolution. And also we are having the option, or we are having the facility, our sensors are able to capture the images, our sensors are able to capture the land surface features in different pixel sizes that we generally call it as a spatial resolution. It is very cost effective, time effective. We can easily cover the large area in a quick time of interval with a lower cost than the traditional ground survey methods. Okay. So when we talk about the image interpretation, generally there are two types of image interpretation. One, we call it as a visual image interpretation, in which we visually analyze our images, whether it is a hard copy image or any kind of digital images. Okay, so visual image interpretation is performed on the digital images. We have to apply different image interpretation keys. We have to apply different elements of image interpretation to get desired information, to retrieve some useful information from the digital images. And sometimes we need to apply some image processing techniques to enhance the quality of our images. If it is not easy to visually interpret our images, so sometimes we need to apply, or we can apply different image processing algorithms on the digital images so that it improves the quality and interpretability of the user. So visual interpretation is just a kind of, you can say, the visually whatever we are getting from the images, and digital image processing is a kind of method that in that we apply some algorithms, some tools. We use different processes on the satellite images to get some desired information. Okay. So image interpretation may be of two types, qualitative and quantitative. Whatever the information we get from the images, if it is in terms of some numbers, then we call it as a quantitative information. And if there are different land surface features, different landscape features or earth surface features are there, and we are able to identify the objects, then such kind of information is known as qualitative information. Okay. So generally, 9 image interpretation elements was proposed by Charles Olson in 1960. You can see here the complexities of the image interpretation keys, the increasing complexities with respect to the resolution. Okay, so tone, color, shape, size, texture, pattern, height, shadow, association. These are some of the interpretation elements, and you can see the increasing complexities in terms of the image resolution, whatever the image we are using, and if we are having different resolution images, if we are using the images at different spatial resolutions. So depending on the resolution, we are also having, or we can face the complexities in the identification of the features or the identification of different landscape features. Okay, so these are some of the commonly used image interpretation keys or the elements of image interpretation. So we generally use the shape, size, tone, the site, texture, shadow, association, and the pattern. Shape is related to the outline of any object, the boundary of an object. Depending on the boundary of an object, depending on a specific shape, we can easily identify the feature, whether it is a natural feature or man-made feature. Each and every object on the earth surface having certain boundary, having certain outline. So depending on the outline, whether it is a fixed pattern, whether it is a fixed outline, then it is a kind of man-made feature. If it is irregular shaped outline, then we can call it as a natural feature. Size is related to other feature. If we are going to compare two different objects on the earth surface, in that case, size is very important. Size is the relative comparison of different features, different landscape features. Tone is related to the color or the brightness value of that object. Sometimes site-specific information is helpful to identify the objects. Some features only exist at a specific sites, like you can call it as a coastal regions. Some features only exist along the coastal region. Some features only exist along the glacial areas. So depending on the site, you can have specific features. Some features or some landscape features are site specific. Then texture is also very important. Texture is the relative change in the frequency of brightness value. Okay, there may be the two types of textures, whether it is a smooth or coarser. If the frequencies, or you can say if the brightness values are changing very fast, okay, that may be considered as a coarse texture images. Means if there are features, or you can say if there are different features, so there may be different brightness values. So there may be the change, or you can say the sudden change in the brightness value of different pixels, showing different class, different features. That will have the coarse texture image. Smooth texture means if all the features are of the same type, if all the features are having the same kind of brightness values, so such kind of images, such kind of areas are considered as a smooth texture. So smoothness and coarseness are very much useful to detect the homogeneous areas or heterogeneous areas. If the image or if the area is composed of different heterogeneous categories, then it will have coarse texture. If the area is having homogeneous features, if the area is composed of homogeneous landscape features, then its texture will be smooth and it will show the homogeneous area. Shadow is very important. Sometimes if we are using the satellite images of you can say the urban area, so the height of the building or different infrastructure, different urban features are having some kind of height, so that will be studied on the basis of the shadow. Association is very important. It is a kind of relationship between two nearby spatial features. Association is very useful to identify object that is having some specific relationship with another object nearby that area. Like if we are working in a agricultural land, or if we are working in an area there is a river, so there may be the spatial association between the river, the water bodies of the river, and the associated sand area, because sand generally exists along the river. Okay, so if we are having a white color patch on the image and it is along the river, so definitely we can use the association rule. We can use the association feature to locate or to identify that feature, whether it is a sand area or not. So association is a kind of spatial relationship between different features exist on that area, and pattern is directly related to the, you can say, if the feature is man-made, it will have some fixed pattern. If the feature is naturally covered feature is there, then it will have non, then it will not have the fixed pattern. So the pattern tells us the, you can say, the arrangement of the features, arrangement of different landscape features, or arrangement of different objects in an area. Okay, so moving to the next slide, these are some of the typical examples of image interpretation. Okay, when we are going to use some images over the urban area, so these are some of the commonly identified objects over the study area that is highly urbanized. There may be the airport, then beach, bridges, commercial areas, farmland, football. So you can see the type of the objects, and when you compare different objects, so you see the different objects are having different color, they are having different shape, and they are having different size, they are having different pattern. So depending on the shape, size, pattern, association, the smoothness and coarseness of the object, we can easily detect and identify different landscape features in an area, whether it is an urban area or non-urbanized area, or it may be some glacial area, it may be some coastal region. Depending on their color, shape, size, tone, texture, their association, we can easily identify different objects. Okay, image interpretation methods may be done, or there are two different ways for the image interpretation. We can apply manual procedure, as well as we are having different computer based algorithms. As we have already discussed, sometimes it is required to apply some algorithms on the images that will come under the digital image processing. Okay, so computers are equipped with different algorithms. By applying different algorithms, we can get the information, if it is not possible to get the information visually. Okay, so manual procedure includes the visual image interpretation. We analyze the images visually and try to identify different objects based on their shape, size, texture, pattern, shadow, association, whatever the elements are there. Okay, but sometimes if it is not possible to get some desired information, or sometimes we are having low quality images, so we need to apply some computer assisted procedures. We need to apply some computer based algorithms to process our satellite image. So it will be, now we will be able to identify different features. So it is some kind of statistical analysis. Then we can have different types of mathematical models. We can apply different image enhancement and different contrast stretching method, different machine learning algorithms and classification methods are there that can be applied to get the information from the digital images. Okay, so these are the basic principles that should be involved in the image interpretation when we are going to interpret our images. So these are some of the basic principles that should be taken into consideration. Okay, so as we already know that image is a pictorial representation of different landscape features. Okay, so when we talk about the pattern of different features, so pattern includes the physical property, the biological property, as well as the cultural relationship between different objects. As different objects reflects in different manner, or you can say when we talk about the spectral response pattern is different for different objects. Okay, but if we are getting the same kind of reflectance, same kind of spectral response pattern So we can say that there are same kind of object. So depending on the spectral response pattern, depending on the spectral energy, we can get that whether it is a similar object or non-similar objects. Okay, so there is required to apply some systematic examination. We have to adopt a systematic examination for getting information using any satellite image or any aerial photographs. Okay, and whatever the information we are extracting from the images, or whatever the information we are collecting from any digital image, any satellite image, is based on the knowledge, skill and experience of the analyst. Whatever the person who are using that image, if he is well equipped, he is having good knowledge, he is having good interpretation skill, he is very experienced person, so it can get more information. So depending on your expertise, depending on your skill, or depending on your knowledge, you can get more information. So information extraction is directly proportional to your knowledge, directly proportional to your experience, or directly proportional to your skill, and what kind of images or what kind of methods you are applying, what kind of equipments you are using to get the information from that image. Okay, so these are some of the common factors that governs the interpretation ability of any user. Okay, as we are the user, we use different satellite images for various applications. So these are the commonly identified factors that governs or that controls the interpretability or interpretation ability of any user. I already discussed that training and experience. If you are having more experience, if you are well trained, so you can get more information, you can retrieve, you can extract more information from the satellite images, and what kind of object or phenomenon you are studying, what kind of photographs or digital images you are using. If you are using high quality images, like if you are using high resolution images, so definitely you will get more information in comparison to the images with the low resolution. So quality of your photograph and quality of your images, spatial resolution of your image, helps us to get more information. Then what kind of equipment, what kind of softwares and methods you are applying for get the information, what is your interpretation keys, what kind of interpretation keys you are using. And means if there are total 8 interpretation keys, if there are total 8 elements of interpretation keys, so how you are going to use the key which is useful, or how you are going to use appropriate interpretation keys if you are interpreting any images. And if you are having some prior knowledge, if you have already visited that study area sometimes, or if you are already get some ground data sets, you visited the place many times, so the prior information or the prior knowledge of that study area helps you to identify different objects. Means you should be well aware with the study area. If you are well aware with the study area, then you can get more information in comparison to some other person who are not having the prior experience or prior knowledge of that study area. Okay, so these are some of the factors that can govern or that can affect your interpretation skill, your interpretation abilities. Okay, so these are some of the techniques that can be used for the visual image interpretation. The development of your interpretation has mainly by the empirical methods. We generally use different empirical methods, and there may be some gap between the photo images on one hand and the reference label. Sometimes we need to have some reference label. If you are interpreting any image, if you are analyzing any satellite images, so sometimes it is very hard to identify the objects. In that case, you need to have a reference image, or you need to have a reference information, and on the basis of that reference information, that reference image or reference map, you can get the option, you can have the more option to get the information. Okay, so most of the techniques adopted for the image interpretation may be used for different disciplines. Sometimes you need to study different disciplines. If you are analyzing images, if you are analyzing any digital image, so sometimes you need to study the forestry, sometimes you need to study the agriculture and other disciplines. So image interpretation also involves the use of different disciplines, use of different branches of the science, different methods that can be involved in the image interpretation. And also it is having a sequence of activities, and you have to search for new methods, you have to search for new algorithms, new techniques that will help you to visually interpret your digital images. And also you can modify the existing methods, you can modify the existing techniques to get more detailed information from that digital images. Okay, so the image interpretation can be done at 3 different levels. Okay, when we are interpreting any images, when we are interpreting any kind of digital image from the optical sensor or microwave sensor, it can be performed at 3 different levels: the measurement of your object, measurement or identification of different objects present over that study area, and what kind of appropriate measures, what kind of appropriate methods you can apply to get the information from that images to solve any problem. Okay, so image interpretation method, or you can say the process of the image interpretation, involves at 3 different levels. It involves 3 different stages: measurement of the object, identification of different objects and features, and appropriate method or appropriate element of the visual interpretation to get the information from the images to solve any problem. Okay, so the image interpretation methods totally depends on the kind of information to be interpreted, what kind of information you get, or what kind of information you are planning to retrieve from the images. If you are getting, if you want to get more detailed information, so definitely the high resolution images are required. So depending on the level of information, or depending on the type of information you want to get from the images, you need to go for high resolution images or medium resolution images or some coarse resolution images. How much accuracy you want? Okay, definitely if you are working on urban area, so high resolution images can help us to get more accurate information. So accuracy depends on the type of images you are using for visual image interpretation. The reference level, what kind of reference information you are having. If you are getting some problem to identify different objects, and if you are referring some existing information, you are having some reference information. So what kind of reference information you are using, and what is the validity and what is the accuracy of the reference information, and what kind of imageries you are using. It is very important. If you are using high resolution or low resolution images, if you are using panchromatic band or multispectral band, hyperspectral bands, hyperspectral images. So depending on the type of the imagery, depending on the type of the photographs available, also helps us to develop new method, also helps us to identify different objects. Okay, scale is very important. At what scale you are planning to get the information from the images, and what kind of external knowledge is available that can be used to identify or to accurately validate your results. Okay, so image interpretation method, or the entire process of visual image interpretation, based on these are the factors. These factors are very important to develop a methodology or to develop a process for the image interpretation. Okay, so these are the commonly used activities. These are common activities of the image interpretation: detection, recognition, analysis of different feature, deduction, classification, idealization, and convergence of the evidence. So when we start from the detection of object, then we can recognize the name and type of the object. Then we can analyze the recognized objects for various applications. We can have some kind of, we need to reduce the type of the recognized objects. Then we can go for the classification of different objects, classification of different features. Then we can develop some idea. We can get some ideal, or you can say we can get some normalized information from the images, and we can go for lastly for the convergence of evidence. If we get suppose if we have identified an object, so what is the evidence of the existence of that object in that area? That is very important. You have to validate your result. if you have identified that there is a forest area, there is some kind of minerals are there. So what is the evidence of the existence of that object in that area? It is very important. Okay. So whatever the analysis we are going to use, or whatever the analysis we are using for image interpretation, you should work methodologically. We should adopt some methodology that will that will help us to get some general information. Okay. And the fishing expedition and the logical search, sometimes we need to examine each and every object, but sometimes it is not required to get each and every object. So in that case, we can have some quick search, we can get for some quick scanning or quick analysis of that image for selective or particular study. So depending on the requirement, if we want to get detailed examination of the images, then we can go for the fishing expedition. And sometimes we need to just go for selective study. We need to go for selective identification of the features. Then in that case, we have quick scanning or quick analysis, quick examination of that images. Okay. So these are some of the types of image interpretation keys: item key, subject key, regional key, and analogous area key. So this, here you see the scope when we talk about the image interpretation. So scope, what is the scope of your image interpretation? What kind of item you want to identify, means what kind of features you want to identify, how many types of classes you want to identify, and how many types of classes you want to classify for land use land cover mapping. What kind of subject area you are working on. If you are working on forest, you can working on different types of other fields. Regional keys, some features only exist in a regional area, some landscape features only exist in a particular area. So you need to apply the regional keys. Regional keys means you should be well aware with the fact that this feature only exists in a particular area, in that specific area, in your study area. And sometimes we need to go for the analogous area key, like sometimes you need to go for some analogous method, analog method, that it's very much useful for the image interpretation. And technical and non-technical background, both are important for the image interpretation process. Sometimes we need to apply different techniques, sometimes we need to apply different non-technical methods to get the information. So different technical and non-technical level is required for getting the information for image interpretation. Okay. So these are some of the types of the image interpretation keys: direct keys or association key. Direct key means whatever the element we are directly using. And sometimes we need to develop or we need to use some associated keys. Means associated keys means these are some of the interpretation keys that is derived from the original interpretation keys. Okay. So the manner, whatever the information you are getting from the images, you have to apply different manner. It should be selective or elimination. Selective manner, you have to be very specific for a particular feature. So you can have the direct keys, you can use different image interpretation keys to get the information. And sometimes if you are not working on a selective area, if you are not selective for a particular feature, so you can have different other options. You can develop some other keys, image interpretation keys, to get some information from the images. So these are some of the methods of the analysis and reference level. We can use different types of images. We can use different types of data sets. Sometimes we need to use multi-band images, that is a multispectral images. We generally call it as a you can say the optical images are a kind of multispectral images. Sometimes we need to use multiple images that is acquired from different sensors. Multi-date images like multi-temporal data sets can be required sometimes for monitoring the changes. And sometimes we can have the we can have the option to use the multi-stage images, like we need to use the images acquired by the space-borne sensor or airborne sensor or ground-based sensors. Okay, so depending on the requirement, we can go for different types of images. Either it is a stereo images, we can use the stereo images, we can use some kind of images that is acquired in the multispectral mode, or hyperspectral images can also be used. Sometimes we need to use the images from different sources, images acquired from different sensors. So depending on the need and requirement, we can have the option, we should adopt a particular image of that study area. Okay, these are the commonly used sensors, or you can say these are some of the commonly used data available in the remote sensing. It may be black and white panchromatic image, we call it as a pan image. Then there are different types of color images, or you can call it as a multispectral images, or there may be the option to use the infrared or false color composite images for image interpretation. So there are other options are there. Microwave images can also be used. We can have the option to use the multispectral and hyperspectral images can also be used for different applications. Okay, so this is the element, these are the elements of image interpretation I have already discussed with all of you. Now I'm going to show you how these elements, or how these components of the image interpretation can be used to identify different features by having some examples. Okay, so now I'm going to take the example of tone. Tone is very important element of the image interpretation. It's a kind of measurement of the intensity of the electromagnetic radiation, or you can call it as a reflected energy that is captured by the sensor. Okay, so tone is you can call it that measurement of the energy in terms of some reflectance value, in terms of some kind of, you can say, the digital number values. Okay, so depending on the information, depending on the energy acquired by the sensor, we may have different color, we can have the features with different colors. So here you see this is the false color composite image, and on the basis of their tone and color, we can easily identify different features. So here number one is a kind of vegetation. As we know that the vegetation appears red color when we use false color composite images. Okay, then the number two is a water body. Then the number three is a sand. Sand always exists along the river. So here we need to also apply the association rule. Four is the deep water. So this is the difference between there is a difference between deep water and shallow water. Okay, so two is a river that is having also a water body, but four is a deep water. So if it is a clear water, so it can absorb total radiation. In that case, it will have black tone. But if there is some kind of turbidity, if there are some kind of pollutants or mixtures are there, so there may be some kind of reflectance. So that in that case, we will not get the black color for that water body. So depending on the concentration of pollutants, or depending on the depth of the water level, we can have different color for the water. If it is a pure water, if it is very deep, then it will have the black color, black tone. If the water body is having some turbidity, it is having some mixing or some pollutant, then it will not give you the black tone, but it will have some kind of reflectance because of the particles dissolved in the water. So in that case, it will give some other color than the black. It may be some grayish color, or it may have some light bluish color. So on this kind of tone, on the basis of this type of color difference, we can easily differentiate between the pure water and the mixed water. And fallow land is a kind of area that left blank, and it is not having any kind of cultivation, it is not having any kind of crop land. Okay, fallow land is a kind of area that exists within the agricultural land, and these are the agriculturally rich area, but it is left blank during the image acquisition. So such kind of areas are known as the fallow land. So this is the example, or this is the use of tone feature or tone key for identify different features on the basis of their color. Okay, then texture, as we have already discussed, texture may be of two types, smooth and coarse. So if the area is covered with the same kind of feature, then it will have the smooth texture. Features, if the landscape is composed of different features, then it will have the coarser texture. Suppose if there is agricultural land An entire agricultural land is having paddy area or paddy or any kind of you can say the agricultural crops. So it will have the same kind of tonal change. It will have the same kind of value, that is having the smoothness. But if the agricultural lands are having different crops, then it will not give you the smooth texture, it will give you the coarse texture. Coarseness means the features are having different tonal changes. The features are having different frequencies of the tonal changes. So depending on the type of the area, if the entire landscape is covered by the same kind of feature, it will give you the smooth texture, means all the pixels or the features are having same kind of spectral response. But if the area is covered with heterogeneous features, if the area is covered with different types of crops, then different crops will have different values. Different crops will give you different spectral response. So that will have some kind of coarseness, that will provide you the coarse images, or you can call it as a heterogeneous kind of feature is there. Okay. Shape and size, it is already discussed previously that shape and size is very important to distinguish between natural features and man-made features. Depending on the shape, if it is a specific shape, there is a specific shape and size, so it may be considered as a man-made object. But if the shape is irregular, there is irregular shaped area, if irregular shaped feature, then it is considered as a natural feature. Okay, so depending on their specific or fixed boundary, fixed outline, we can get the information whether it is a natural feature, natural object, or the man-made object. Here you can see the difference between the reservoir, that is a natural feature, it is having irregular shape, whereas there is a fishing pond, it's a kind of man-made object, it is artificial object that will having definite shape and size. Depending on the shape and size, we can easily distinguish between different landscape features of natural feature as well as the man-made feature. Okay, spatial pattern, it's a kind of, you can say, the how different objects are there, means what is the pattern of the existence of different features. So if we are using some kind of you can say the images over the urban area, so there may be different urban features, or you can say if an area is there or if it is a heterogeneous area, so there may be different features. Landscape is composed of different features. So what is the pattern of the you can say different features? So depending on their arrangement, you can get the information about the pattern. Okay, if it is having fixed pattern, so you can call it as a some kind of man-made areas. If the pattern is not fixed, so it may be considered as some kind of natural surface. And association rule is very important, as we have already discussed. Sometimes we need to identify an object with respect to its relation with the neighboring feature. Okay, like for an easy example, the existence of sand and the water body or river. The river is a kind of water body. If we will get some kind of white patches along the river, so by applying the association rule, we can have the idea that sand always exists along the river. So if we will get the white patch along the river, so we can definitely call it as a sand, because there is association between the river and the sand area. But if we are having some other white patch away from the river, so that it may not be the sand, it may be some other kind of features, it may be some other kind of class. So association is very important to identify the objects with its relationship with the neighboring feature, neighboring object. Okay. So now I'm going to discuss, I'm going to show you some of the photographs, some of the images to see how different interpretation keys are useful to identify the object. So image interpretation, the main aim of image interpretation is to relate the information acquired from the images to the reality or to the real world. Okay. So this is the picture of a real world. This is a picture of a village. And so it is actual real picture, but When we see this area on the image, it looks like this. This is the aerial photograph of the same area. So interpretation, the main objective, or you can say the aim of image interpretation is to relate the real world objects with the objects that is identified on the images that we can identify using visual image interpretation methods. Okay. Image interpretation can also help us to categorize different objects, or you can say we can have the option to get the information from the features like image characteristics. The image characteristics is very important while we are going for the visual image interpretation. Different images are having different characteristics. Some images are having 3 bands, some images are having 10 bands, 20 bands. In case of hyperspectral, we are having more than 200 bands. So depending on the image characteristics, we can have different level of the information while we go for the visual image interpretation. Okay, so in sometimes we need to apply these 4 characteristics of any image. Spectral characteristics, these are kind of spectral resolution. Spectral resolution is the number of bands that is used to acquire the information about that study area. Spatial resolution is the ability of any sensor to distinguish 2 objects. Stereo characteristics is the way how we acquire the images over the same area at 2 different angles. That will provide you the stereo information. This stereo information will be helpful to develop 3-dimensional model of that area. And sometimes we need to apply associated information of that image. Sometimes we need to have some reference information, reference map that will be used along with the image. And we can use spectral, spatial, and other information acquired from the images to get or to identify different features. Okay. So gray, tone and color. Tone and color is a kind of, you can say, these are the elements of visual image interpretation, and these are directly related to the spectral information. Depending on the spectral information, depending on the spectral characteristics of that image, we can have 2 elements that is call it as a tone and color. So tone and color is directly related to the number of bands, or the, you can say, the images acquired in different spectral bands. Okay, this is the typical spectral response pattern. Depending on the spectral response pattern of different features in different wavelength intervals, we can have the information about the object. Depending on their spectral response, we can have the option, or we can easily identify the object, whether it is a vegetation or non-vegetation, water bodies, or any kind of other feature is there. Okay. These elements of visual image interpretation, shape, size, shadow, pattern, and association, these are related to the spatial characteristics of an image. Okay. Spatial characteristics means the ability of any sensor, ability of any image to distinguish 2 close objects. So the shape, size, pattern, texture, these are the visual image interpretation keys, and these are directly related to the ability of any sensor to distinguish 2 close objects, that we call it as a spatial resolution also, or spatial characteristics. Okay, so these you can see these are the different gray levels. Like these are the different levels of the gray tone images. Depending on the, if we are using a gray image or black and white image, depending on their gray tone or the variation in the gray tone, we can easily identify different objects. Here you see there are different objects, and different objects are having different gray tone. A, B, C, and D. A is a farmland, it is having different gray tone. B is a river, it is having different gray tone. C is the kind of sand. D is the water bodies. So depending on their variation, depending on the variation in the gray tone, we can get different objects. We can easily identify different objects. Okay. So you see, this is another example how we can use black and white image or panchromatic image to get or to detect, to identify different objects on the basis of their variation, on the basis of the variation observed in the gray tone. Okay. This is another example how we can see the difference or how we can monitor the changes on the basis of their gray tone information. Okay, this is the way how we can detect the shadow and cloud. Okay, so sometimes because of misinterpretation, some user identify the shadow as a water body, but you have to be very careful about the uh, shape and color of the shadow as well as the water bodies. Shadow and water bodies both appears as a black tone, but you need to be very careful. You cannot, you can say that you misinterpreted the shadow as a water body or a water body as a shadow. So, and it can be done by having some experience. It can be avoided by having experience and knowledge about the study area or some experience. Okay, this is the difference between the false color composite, or you can say the true color image and the panchromatic image. So this is the image of the same area visualized in two different ways. One is in the true color, one is in the panchromatic image. So you can have both the options to visualize your image in the panchromatic band, that is only having single band or black and white image. And also there is a option to visualize your image in the true color. Means true color means whatever the feature is there, it will be appeared in the color what is in the real world. That will consider as a true color image. So true color images and false color images or panchromatic images are used for the visual image interpretation, but you should be very careful about the color. In panchromatic, you can have only black and white color, but when we use the true color and false color composite images, we can have different colors. We can have the option to identify the objects on the basis of their tone and the color. Okay. Shape and size is very important. Each and every object in the real world having definite shape and size, and depending on their shape and size, you can have the information whether it is a man-made feature or natural feature. It is already discussed with all of you. So these are some of the fixed shape, or you can say these are some of the pattern, or you can these are some of the objects having certain shape and size. So depending on their pattern, depending on their shape, depending on their size, you can easily identify whether it is a natural feature or the man-made feature. Okay, this is another example of the how the shape and size is useful to identify different objects. Okay, this is a kind of, you can say, some feature man-made features. These are some man-made objects that is having fixed shape. Okay, so depending on their shape and size, you can identify the object, whether it is a man-made or natural or some other kind of feature is there. Shadow is very important to get the information about the object having some height. Okay, if you will get the shadow in your image, so definitely you can say that there is a object that will have some kind of height. Okay, so shadow is very important to identify the features, identify any infrastructure or any object in the urban area or any other area having certain height. But in that case, you have to be very careful whether it is you are using high resolution images or low resolution images. So the shadow, or you can say the high resolution images acquired from the Iconos or QuickBird, that is having the resolution up to 1 meter, you can definitely get the shadow area. But in Landsat images or any other medium resolution images, it is not possible to get the height of that object, height of that building or any other feature in that area. So for for identification of the height, for detecting the height of an object on the basis of the shadow in the image, you should go for high resolution images that will have the spatial resolution up to 1 meter or less than 1 meter. Okay, this is another example. Means this is the object in the real world. This is some kind of object having some height. That is the way how it looks in the real world and how it looks in the aerial photograph. Okay, so you can correlate, you can see, you can have the option to correlate the object in the real world as well as how it looks like in the aerial photograph or any kind of high resolution images. Okay, this is another example of the uh, identification of objects on the basis of their shadow. You can see here the A, B, C. These are the areas having some shadow. Means there are some objects having some height. You can see these are the trees having some height, and you can see the area A, which is written here as a is a kind of shadow of that, of these areas, shadows of these trees and these objects. Okay, this is another example how you can use the shadow of an object to get its height, to locate the building with some height. Okay, these are the examples of the aerial photographs, or that you can call it as a high resolution photographs acquired from the aerial sensors, or some kind of photographs from the airborne sensors. Okay, this is another example. This is object identified on the image and how it looks like in the real world. Okay, so image interpretation, it means the objective of image interpretation is to relate the object in the real world and how it looks like and what is the way it is looking, it is observing in the satellite images. Okay. Okay, this is same kind of object in the real world picture and how it looks like when we observe it in the digital image having some high resolution object information is there. Okay, so this is the you can say this is the this is normally used process in the remote sensing. Okay, now I'm going to show you the impacts of the resolution. Means how the resolution of the images are affecting our image interpretation abilities. So as we are very well aware that there are four kinds of resolution, that is spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. Okay, so resolution strongly affects the interpretation abilities. Your interpretation skill, your interpretation options are strongly affected by the types of the resolution, or what kind of images you are using, what is the spatial resolution of that image, what is the spectral resolution of images. These four characteristics of an image strongly affects our interpretation ability, our interpretation skill. Okay, so now it is very important to see what is the difference between detection, discrimination, and identification. There is slight difference between the detection. When we talk about the detection means we are detecting the spectral signature, spectral response from the objects of the interest. Okay, discrimination means how we are differentiating different spectral response coming from different objects, and identification means on the basis of their spectral signature, on the basis of their spectral response, we can easily discriminate, we can easily identify different features, whether it is a vegetation or other kind of urban areas, water bodies, soil, and other kind of crops are there. So this is the difference between the way of the detection, the discrimination, and the identification. So we start with the detection, then discrimination, and finally we identify different objects on the basis of their spectral response when we are using multispectral images. That is a kind of spectral energy captured by the sensor in different wavelength intervals. Okay, so spatial resolution is very important for identify different objects. It is strongly affecting the spatial resolution as well as the interpretation skills. So the spatial resolution is directly related to the instantaneous field of view. It is the way, or it is the angle through which the sensor is acquiring the images over the earth or over the surface area. Okay, and the instantaneous field of view determines the dimension, and that is directly related to the ground resolution cell, what we call it as a pixel size or the pixel. Ground resolution cell is the area that is imaged on the earth surface, and that is having certain width and height, and depending on the ground resolution cell, we can have the images with different spatial resolution. Okay, so how small a ground resolution cell do I need? Means what kind of pixel size is useful, and how this ground resolution cell is affecting the size of the pixel or the spatial resolution of an image. Okay, so ground resolution cell, we call it GRC. That is very much similar in the concept of the ground sample distance. So this is the way how we can object, or how we can identify different objects of the same size with using the ground sample distance as GST. Okay, so you see these are the squared shaped pixels. Okay, squared shaped pixels. So each pixel is having certain width and height that we call it generally as a pixel size or the spatial resolution, and it depends where the pixel falls in relation to the object of your interest. Okay, if your object falls within one of the pixel, then it will be very easy to identify that object. But if your object of interest falls in an area that is covering all the pixels, so it will be difficult to identify that object. Okay, so this is the difference between the use of different spatial resolution images. So in the first option, in the first figure, you see the entire object is falling under a one pixel. So these objects will be very easy to identify. But if the same object is falling and covering all the nearby pixels, so it may have the contribution from different pixels. So it will be very difficult. It will be a little bit difficult to identify or to detect the object. Okay, so this is the effect of the spatial resolution, or you can say this is the effect of the pixel size, and how the pixel size is affecting the image interpretation, how the pixel size is affecting our ability to get some useful information or to identify different objects on in the images. Okay, now this is the thumb rule. This is the same thing which I have already discussed, that depending on the pixel size, depending on the width and height of a square shaped pixel, you can have different types, different details, different levels of the information. Okay, that is a general rule of the identification of the objects on the basis of their pixel size or the pixel. Okay, so this is another kind of example how we are developed from 1 meter ground spatial resolution images to like we are having 1 feet ground spatial resolution images. That is very much useful to identify different objects. So you can see the comparison between the 1 meter spatial resolution images and 1 feet spatial resolution images. That will be very much useful to identify and to get information, detailed information about objects. That will help us to get more detailed information when we are using visual image interpretation. Okay, this is the way how the pixel size is affecting the mixing problem. Okay, depending on the pixel size, we can have the option, we can have the problem, or you can say we are having the option to identify the objects, whether it is a mixed object or you are able to identify the feature separately from other features. Okay, so spatial resolution keeps growing, keeps getting better. Depending on the spatial resolution, we are having the abilities to detect different features that will certainly help the interpretation abilities of any user. So if we are using high resolution images, definitely it will be very much useful. It will help you to identify different features. And if you are using some kind of coarse resolution or medium resolution images, so it will be little bit difficult to identify the objects. So image interpretation skill is depending on the type of images or the type of spatial resolution images you are using for different applications. This is the example. This is the way how you can see what is the effect of the spatial resolution on your interpretation abilities, on your interpretation skill. In 4 meter, in 2 meter, in 1 meter spatial resolution images, you can see how well you can identify different objects, how well you can detect different features when we are using 1 meter spatial resolution in comparison to the 4 meter spatial resolution. Okay, This is another example of using different spatial resolution images that will be helpful to identify different features, the shape and size of different features. Even you can also apply the shadow rule to identify or to detect the height of that building. Okay. These are some ultra high resolution images are now available, but this is not for the civilian purpose. It is only for the military and defense purpose. Now the images up to 6 inches, 15 centimeter is now available. That is very much useful to identify the objects. This is the example how the spatial resolution is affecting our interpretation abilities, and eventually it will affect our classification accuracy. So here 3 images with different spatial resolution, A, B, and C are the images with 5.8 meter spatial resolution. Image B is the 30 meter spatial resolution image, and image C is the 56 meter spatial resolution images. So depending on the spatial resolution of images, it is very difficult to identify the objects, and eventually if you are not able to identify different features, so it will also affect the accuracy and details of your land use land cover map or any kind of classification. So you see, when we use high resolution images, it will provide you detailed information, detailed land use land cover features in respect to the images with 30 meter spatial resolution. And again, in the last image, that is image C is having 56 meter spatial resolution. So in the 56 meter spatial resolution, you will not get more detailed information about the objects. That will hamper your interpretation abilities. That will hamper your interpretation for different objects, for identification of different objects, and then eventually it affects your classification accuracy, and your final output product will have less details in comparison to the images with the high resolution, high spatial resolution. Okay, this is the way how we are having different spectral wave bands of Landsat images. This is Landsat TM images that will get the information in 7 bands, and depending on the number of spectral bands we are using, that will also help us to visually interpret our image effectively for getting the information, for identifying different features of our interest. Okay, so this is the example how different wavelengths or different bands can be used, and how different wavelength intervals can be used to identify different objects on the satellite images. That will help us to interpret our images with accuracy and with good details. That will eventually help us to get more detailed or more accurate land use land cover maps and other information from the images. This is the way how we can use the hyperspectral. Hyperspectral is the continuous arrangement of the spectral band, already discussed by Dr. Prashant sir, that spectral resolution is continuous in case of hyperspectral images. So that will also help us to identify more more detailed information, or you can easily discriminate between different species, different crop types, while we are using hyperspectral images that is having a more number of bands in comparison to the multispectral bands. Okay, so there is a trade-off. There is a, you can say, this is a commonly used common rule is that high spectral resolution generally has lower spatial resolution. Okay, so if you are having high spectral resolution, its resolution will be low. If you are having high spatial resolution, your spectral resolution will be low. Both are, you can say, inversely proportional to each other. Spectral resolution and spatial resolution both are inversely proportional to each other, and this is the kind of trade-off that is available, that is in remote sensing community. Okay, radiometric resolution is the sensitivity of detector, and how sensitive your detector is there, and how the better you can detect different objects. So sensitivity also helps us to get more accurate information about the objects, and it will also help you to get more detailed information while applying visual image interpretation keys. Okay, so high radiometric resolution means it is very important to get some quantitative information about any objects. You can easily identify sea surface temperature and different types of objects can be identified when we are having high radiometric resolution images that will have more sensitivity to detect the incoming energy coming from the object, coming from the Earth surface, and that is captured, that is sensed by the sensor. So these are some of the uses of different image characteristics for visual image interpretation. Thank you very much for your kind listening this lecture. If anyone have any question, then you can ask.
Sir, good afternoon.
I'm not getting your voice. Yes.
Hello, sir.
Yes. Yes.
Sir, good afternoon.
Yes. Good
Sir, are
afternoon.
pixels and digital numbers are same?
Sorry, I'm not getting your voice.
Sir, pixels and digital numbers are both same or different?
A pixel value or digital values both are same.
Okay.
Yes, Bhavna.
Sir, the shape of
Pixel
pixels.
values, digital number values, brightness values, all are same.
Okay.
All are same.
And sir, one more question.
Yes.
Sir, we can
आवाज आपकी डिस्टर्ब होके आ रही है.
consider the shape of pixels are always square.
सॉरी, आवाज नहीं आ रही. आवाज भावना.
सर अब क्लियर है?
माइक इज म्यूट.
सर अब क्लियर है?
हाँ बोलिए. हाँ. Yes.
And sir, the shape of pixels we considered are always square. Why not circular?
Generally it is square shaped.
Yes, sir. Why not circular or triangular or any
Generally it is
other?
square shaped. Yeah. Actually, what happens, generally, whatever the ground resolution cell is in square shaped, because the dimension that we call it as the width and height of that pixel should be equal for getting better interpretation or for getting better information about the objects. So
Okay.
if it is a circle, so definitely some areas will not be covered by the circle. Okay, it may
Okay.
left some area, so that will be hampering our interpretation. But if we are having some squared set pixel, it will cover a specific object very accurately in comparison to the rectangular and circle shaped pixels.
Okay, sir.
Any other question from anyone?
सर अंशुल दिस साइड.
Yes, Anshul.
सर जो भी आपने बताया एक बिल्डिंग थी उसकी हाइट जो है वो प्लान में कैसे आप डिपिक्ट करवा पा रहे हो, वो एक बार फिर से बता देंगे सर?
किस में?
सर ये अभी जो आप स्लाइड्स दिखा रहे थे उसमें एक बिल्डिंग की हाइट थी, तो वो प्लान जब हम ले रहे हैं सैटेलाइट इमेज उसमें वो 2D में आएगी, तो उसकी शेडो कैसे आप डिपिक्ट करवा पा रहे हैं कि वो हाइट शो कर रहा है वहां पे?
नहीं, तो वो आपका जो हाइट है, हाइट विल बी देयर व्हेन देयर इज अ डिफरेंस एंगल ऑफ द इमेज एक्विजिशन एंड द सन इज एट द डिफरेंट एंगल. अगर सन दूसरे एंगल पे है और इमेज दूसरे एंगल से लिया जा रहा है, जो सेंसर का एंगल
ओके
है,
सर, ओके.
तो वो दूसरे एंगल पे है और सन का एंगल दूसरा है, तो बोथ आर इन द अपोजिट डायरेक्शन. इन दैट केस we can have the images and that will have shadow, and by having some mathematical calculations, by having some mathematical geometrical application, geometry is there, by having some angle of incidence of the rays and the other kind of mathematical equations can be used to get the height of the building.
Okay sir, thank you sir.
Anyone?
Sir, I have a question.
Yes.
Sir, which one is better, Iconos or QuickBird in measuring the height of an object?
Iconos and QuickBird both are having, you can say, spatial resolution, a very good spatial resolution. Depending on your application, you can go for Iconos or QuickBird. Both are good, but depends on your application or depends on your availability. I think this QuickBird is better than Iconos. QuickBird is having more better spatial resolution in comparison to Iconos. So you can go for the QuickBird data sets.
Okay, sir.
But it
Thank you, sir.
also depends on if there is availability. If there is availability, then you can go for any of the sensor data.
Okay, sir. Okay, sir.
Anyone?
सर मेरा एक और क्वेश्चन है
Yes.
सर हाइपर स्पेक्ट्रल रिमोट सेंसिंग में जो हम इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम की बात करते हैं तो वो हम कॉन्टिन्यूस मतलब बोलते हैं कि कॉन्टिन्यूस आता है वो
Yes. Yes.
सर बट सम एरियाज ऑफ इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम आर सम एरियाज आर नॉट इवन मतलब जो यूवी और एक्स रेज होती हैं वो कई बार हम वो एब्जॉर्ब नहीं होती तो फिर वो कॉन्टिन्यूस कैसे आता है
नहीं तो अल्ट्रावायलेट इज ऑलरेडी एब्जॉर्ब इन द अपर एटमॉस्फेयर, तो अल्ट्रावायलेट
Okay.
बैंड तो हम यूज ही नहीं करते हैं। वो तो जो सेंसर हमारा है, सेंसर इज डिजाइन इन सच अ वे दैट इट कैन ओनली कैप्चर द विजिबल पोर्शन ऑफ द इलेक्ट्रोमैग्नेटिक रेडिएशन। और जो सोलर रेडिएशन है जब वो एटमॉस्फेयर में एंटर करता है तो उसका जो अल्ट्रावायलेट एंड गामा एंड एक्स रेज जो शॉर्टर वेवलेंथ्स हैं वो ऑटोमेटिकली एब्जॉर्ब हो जाती है अपर एटमॉस्फेयर में। सो वो हमारे अर्थ तक पहुंच ही नहीं पाती है। जब अर्थ पे नहीं पहुंच रही है तो जब वो रिफ्लेक्ट नहीं होगा अर्थ पे पहुंच के तो फिर द सेंसर हाउ द सेंसर कैन कैप्चर दिस अल्ट्रावायलेट एंड अदर शॉर्टर वेवलेंथ्स।
यस सर तो फिर सर कॉन्टिन्यूस कैसे हुआ वो
Continuous in sense we are having the visible portion that is having different wavelength intervals, blue, green and red. Suppose the range of the blue is 0.4 to 0.5, okay,
okay
0.4 micrometer to 0.5 meter, and the green starts from 0.5 to 0.6, but there is a gap between 0.5 to 0.6. It should be 0.51, 0.52, 0.53, 0.54, 0.56, so that it can reach up to 0.6. In multispectral, it is having discrete bands, that is 0.4 to 0.5. Then next band will start directly from 0.5 to 0.6. But there is a gap between 0.5 to 0.6. That will be a gap that will be filled by the continuous spectral band provided by the hyperspectral sensor. ठीक है?
ओके ओके सर
क्लियर और हैविंग सम डाउट?
नहीं सर ठीक है समझ आ गया थैंक यू सर
ओके थैंक यू। सो if anyone have any question then you can ask.
और कोई कुछ बचा है पूछना है? देखो ये जो सेशंस हो रहे हैं ना, जो एंड सेमेस्टर का डेट शीट भी आ गई है हमारी, ठीक है ना, तो बहुत सारे क्वेश्चंस जब आप लिखते हो तो रिमोट सेंसिंग एज एप्लीकेशन फील्ड आपकी बेसिक्स पढ़ा रहे हैं, जो आपने रिमोट सेंसिंग, जीआईएस, जीपीएस जो आपके फर्स्ट सेमेस्टर में है वही सारी चीजें अपन पढ़ा रहे हैं, और उसी में एडवांस एंड एप्लीकेशन है। तो आपका तो बहुत लोगों को टेंशन आ रहा होगा कि अरे एंड सेमेस्टर में कैसे करेंगे, यहाँ पूरा दिन है, तो पूरा दिन तो यही पढ़ रहे हो। और रिमोट सेंसिंग में तो रट के पढ़ने वाला कोई चीज नहीं है, मैं तुम्हें पहले बता दूं। इट इज ऑल अबाउट कॉन्सेप्ट। कॉन्सेप्ट क्लियर है, आपको जिंदगी में पढ़ने की जरूरत नहीं है। कॉन्सेप्ट क्लियर नहीं है, रटने की जरूरत है, तो समझो कि एक सेमेस्टर में सिर्फ रिजल्ट्स निकलेंगे और कोई फायदा नहीं होगा। तो इसलिए कल एक दो बंदों का मेरा था क्वेश्चनर कि सर एग्जाम आ रहा है, टेंशन हो रहा है, तो इसलिए टेंशन लेने की जरूरत नहीं है। आपका टेंशन हटाने के लिए,
यही चीज तो एग्जाम में आना है, यही चीज तो एग्जाम में आना है।
इससे अलग थोड़ी ना आएगा जी। अब जैसे मान लो जीपीएस आपको किसी ने बताया कि कितने बैंड्स हैं, क्या है, ठीक है ना, तो यही है ना जो आते हैं एग्जाम में, चाहे जीआईएस है, कॉन्सेप्ट्स है, रिमोट सेंसिंग कल इसने बताया, इलेक्ट्रोमैग्नेटिक आज हाइपर स्पेक्ट्रल हो गया, फिर एलिमेंट्स ऑफ विजुअल इंटरप्रिटेशन हो गया, ये जियो साइंस भी आ गया, कल आया आपका जो वाटर पोटेंशियल और कैसे डिफरेंट जियोमॉर्फोलॉजिकल फीचर्स दिखेंगे। तो इट्स ऑल अबाउट ड्रेनेज, डेंसिटी दिखाया उसने, हीट दिखाया। तो ये डायरेक्टली मतलब अगर आप देखोगे तो वी हैव डिजाइन्ड अ वेरी हाई एंड दिस and for the participants I feel that most of them are already started working on their project. They are into my regular contact, and some of the fellow members जो participants हैं they are not feeling well, so they have given their medical reports, but still they are attending it online, and they have stated that they will be completing all the assignments that has been prescribed by the DST as well as from us. They will be conducting it. So again, I take this privilege to thank Dr. Varun Narayan Mishra, a faculty from Center for water resources and climate change, Suresh Gyan Vihari, University, Jaipur, Rajasthan, that he has enlightened us with his special talk on temporal different resolutions that are used in satellite remote sensing, as well as the advantage and disadvantage of basic concepts of images, as well as elements of visual interpretation, whether you talk about tone, texture, shape, size, pattern association, shadow. So he has covered all the topics with examples, and he has very well explained that how different resolutions and this all data sets will be taken into consideration for finally, because at end of the day you are going to have a map that can either be classified using visual interpretation or digital classification. So from tomorrow onwards, you will be moving towards digital classification because they are the high-end classification team. But when you start your career, and still many of the organization agencies in India feel that visual interpretation techniques have a better accuracy than digital. That is a point of debate that always each and every agency has got. And but still, you cannot say that this visual interpretation keys, techniques, and elements are absolute. No, they will exist till this remote sensing and GIS era or subject will exist, because they are the, I can say, the backbone of any classification. Either you do it through digital classification, or you do it through visual classification. Their time consuming, their merits and their demerits is a different altogether point of discussion. But still, a person who has a better classification understanding, who has got a better classification schema template in your mind, that will achieve a very high end product in the form of a nearly 100% accurate classified map. Either it's through visual interpretation or it's through digital classification. So again, I thank Dr. Varun Narayan Mishra, and again we'll meet by 2 o'clock for our hands-on exercises on Saga GS. Meanwhile, you can have your lunch. In case there is any question, you can ask to Dr. Varun Narayan Mishra directly. Okay, we'll meet at 2. So there should be no reminders, no protocol stating that you have to join. Join by 1:55. Okay. So you
Thank
have
you
got.
very much, sir. Thanks a lot.
Hanji,
Thank you,
Hanji.
sir.
Thank you.
Okay,
Thank
then
you.
we will meet again at 2 p.m.
Thank you, sir.
after lunch. Okay, if anyone have any question, then you can directly contact me. अभी बाकी जो हमारे स्टूडेंट्स हैं वो तो डायरेक्ट हमारे पास आके मिल सकते हैं, बात कर सकते हैं. Okay, and you can just contact me through call. Okay. Yes, sir. Can we close it now?
हाँ 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 हाँ